Good morning, John.
Hello,
Hi, can you hear me?
is this who from home?
This is Adam.
Yeah, I cannot talk to you right now. I'm on a conference online and I'll be tied up until 2:30.
Yes, sir.
Okay,
Can
just
you
get Kim to send you the emails I sent to Jeff and see if you can figure it out. But I'm not going to be available until 2:30 because I'm an online conference. Okay.
Okay, but it looks like there's this one Sergey Oliver that's not on the list that might want to be promoted, or no?
Hi. Who's online? Participants.
If you look at the attendees list,
Yeah.
the Sergey Oliver was raising their hand. All right.
Oh,
Charles.
you made the attendees. Yeah, right. Okay. Yeah. Charles is the chair of the first session.
Right, Charles. Yeah, I get that, but see them, Sergey.
Let me, okay. If you go to the last list, okay, the chair is Charles, and then you have the speakers. They are Mark Katzef, Ryan C., Alonso Granados,
Mm-hmm.
Taha
No.
Enkestad, Ryan Cabrits, yeah.
So no, then leave that. Then don't not promote that. Okay.
I do not know Sergey who he is.
Okay. They were just the reason I asked because they were raising their hand several times. I thought they were hoping to be promoted.
I understand that. I just don't see.
Okay, that's fine. I'll just stick to the list.
Yeah, absolutely.
Okay. Sorry about that.
Maybe he's, who is he? Sergio Olivier Simon Cancuya. I'm trying to locate him, but I cannot. Yeah. No, I don't have a Sergey.
I'll stick to the list regardless. That's all I needed. Thank you though.
Yeah, that's safe. That's safer, right? Yeah.
Right.
Yeah, because I've checked and double checked everybody here.
Very
and
good.
the only interesting thing in the list is that there is an invited presentation in the afternoon by the Bell Labs people. I don't know if it's today or tomorrow. Yeah, tomorrow. That has two speakers. But we'll talk about this tomorrow. You don't need to worry about tonight. Today.
Very good.
Sorry.
All right.
Very
thanks.
good.
Yep.
Thanks. This is Adam? Yep.
Yes, it is.
Hi, Adam. Okay. Thanks.
Okay.
And
thanks, John.
Charles is on. We'll see when the others. Hi, Charles. Charles is going to be the chair. Okay, so the first speaker is going to be the dean, Rob Briber.
Mm-hmm.
I told him to be on about 10 minutes before. Then for Ankur, he won't be able to speak, but I have a video that I play from my computer, and then we'll start with Charles. Okay, so hopefully we should be able to keep it so that Charles can start his session at 10:45.
Very good.
Okay, thanks.
Yep.
And I changed the students, and everybody should be okay now. And most of them have verified that the new schedule is fine. I had a scare last night when I started getting, because they did the doodle, and the doodle, yeah, I filled in the doodle myself, assuming that what I'm filling is when I'm available. But apparently, in a very fine print, it said, please indicate when you are not available. So,
oh, geez.
and then half of us went with positive, the other half with negative logic. But anyway, I fixed it.
Okay, sounds good. And sorry about my emails earlier. I printed it out.
No, don't worry about it. You don't understand how much I've gone through in this teleworking environment. I've gone through so much so that nothing anymore scares me. I can prepare for everything.
Right.
You have to have resilience. Nothing else works.
Right. All right. Thank you, sir.
Sure. Thank you. Hi, Charles. Good morning.
Hi, John. Hi, John. I can listen to you now. Good, good.
Okay. Yeah, and I can listen to you. Just try to keep them on time. As you have the slides I sent as far as, instructions. So you have 5 talks. Try to keep them in 20 minutes plus 4 or 5 minutes for questions and answers. You'll be okay. You have a little bit of safety valve on the break, but don't try to go there. Okay.
Say that again, please.
Yeah. Because I've been. Sorry.
You just say something. Repeat, please.
Yeah, you have 5 presentations. Try to keep them each to 20 minutes presentation plus 4 or 5 minutes for questions and answers. Try to keep the time tight, because in these online meetings, if we start going astray, we will go really astray. You have a little bit of a safety valve because you have a break after your session, but try not to go there.
Yeah.
Right.
Perfect.
Yeah.
Yes, I will make sure that everything is there on track. I'm gonna announce that even from the beginning of the session, so that everyone knows.
Right, right. Take 2 minutes at the beginning to tell them, right? Yeah.
I start to announce that after the opening remarks, then I'm gonna check if everyone is there.
Yeah.
Or do you want me to check if everyone is there before the opening remarks? How do you want me to proceed?
No, we're checking. I mean, we're checking. There's a technical person online, Adam. So he's checking, and we'll see when the people come on. Okay. But we will.
I see. Good.
Yeah. This is happening silently as we speak.
No, very good, very good. So the person will let me know before the beginning of the session that everyone is there, right?
He'll be online, I will be online, and we'll be watching all that stuff. I have my mail online, and if somebody's not in, I would try to send some emergency emails in case. But everybody has replied, okay, so should be okay.
Perfect.
We don't have any major. The difficulty will be the first speaker who comes from University of Melbourne, in terms of time difference, right? But it should be all right. It should be late evening there now, okay, or something like that. So.
I see.
Yeah, you see, the first speaker is from University of Melbourne, and the second one is from CMU. That's fine. The third one is University of Arizona, so he's going to be early, and the fourth one is for University of Houston. Yeah, and the last one is from NIWC, okay, so it's power, okay, so this will be okay. But we'll check it, we'll watch it, yeah.
Mm-hmm.
Some of them, they emailed me that they didn't know if they're going to speak live or if they're going to have a video, and some of them have videotaped their lecture, and they asked, I don't know if any of those people are in your session, but they asked me if they could play the presentation from the video from their computer, and I said that's fine. So you should be ready. You should be ready for that if somebody says that, okay? And even one of the opening remarks also will be on video, because the person, our director, cannot be online at the time that we have. Okay, so
good.
Yeah. And thanks for helping, okay? And thanks for helping in more than one ways, actually.
Good. This will be a good experience.
Yeah.
And every conference is going virtual.
It's the first time we're doing it. We're doing this conference online. I had it back in College Park in 2011. And I wanted to bring it back to College Park to have a bigger audience. We'll see what we have. We have done a lot of advertisement. We'll see what kind of attendance we get.
Good.
Yeah. And there are hopefully several new directions coming out of the invited talks, including yours. So that should help.
Good. So you should be starting the opening remark like in 15 minutes.
Yes.
and I see that all questions go to you, you know, I'm gonna emphasize that. I suppose that this email went to every participant, right? That they should send question to you.
Yeah.
And
So all the participants have been emailed the web pages to log in every day. As long as they have registered, then automatically they get the Zoom registration, email. And then they get the email for how to get in. Yeah, right.
Yes.
Yeah.
No, good thing, good thing. And so those questions at the end of the 20 minutes, what happened? You read those questions, or do I ask if anyone has questions? You just read the question, right?
It's up to you. You can actually glance through the questions, judge which, if you have a couple of important ones from the audience, and then you can read them, and then the speaker can answer them, or the speaker can answer them in writing, or you can say, you can unmute the person who asked the question, and they can ask it in person. Okay, you have three options.
So I'm gonna see the question in the chat room in that case, right? In the chat room.
Yeah. Yeah, just say in the beginning. No, it's not in the chat room. You can put them in chat room, or you can put the question and answers. You have two places.
Yes.
You have questions in Q&A, and then you have in chat. Okay.
Yes.
Yeah.
Nice, nice.
But I'll be looking also, so I'll help you if there is anything. But basically, what I prefer usually to do is either read the question or let the person ask it, and then the people can. This takes a little bit of time because you have to unmute them and all that stuff, and then to unmute them, you have to go and make them, because you see, if you go to attendees, you cannot unmute them. You have to make them panelists and so on and so forth. So the easier thing to do is if you can read the question from question and answers or chat, and then ask the speaker to answer it.
I see. So everyone is automatically muted, if I understand.
Mm-hmm. Yes, and actually, if you go and look at, you have two categories of people: panelists, which includes the chairs, me, the technical support person, and the speakers, and then the attendees. The attendees, if you go, they cannot speak, right? So you have to promote them first. So that takes a little bit of time. That's why I say the safest thing to do is you can go to either chat or Q&A, judge the questions you have, or ask your own, and then read them out, and then ask the speaker to answer. You can say, we have a question XYZ from this person, and then please answer it. That's what I usually do. This way it keeps everything tight and you don't lose control.
Perfect.
Hey, John, just to clarify, you don't have to promote them. If you hover over, you should see allow to talk.
I'm at the attendees. How do I make somebody allowed to talk with attendees?
So the attendees, when you
you go to more. Yes, you go to more. Sorry, you're right. If I go to more, then I can say remote.
No,
chat.
There should be.
So I can go to more. Where is that?
Adam, how do I do it? I go to attendees. I go to a name. Oh, allowed to talk. It says yes.
Yeah, and then that gives them the ability to unmute themselves.
Very good. Okay, do you see that?
But at the same time,
where's the button? I go to more.
No. You go to attendees. If you go to attendees and you go over a name, you have two blue spots. One says allowed to talk. The other says more. You can hit the allowed to talk, and then the person can speak.
I see. Where is that? I do not see that on my screen.
You have to, down below, if you click the participants.
Manage participant. I can see manage participant.
You can't see the participants?
I can see on the screen. I can see all the participants. Yes. What do I do from there?
So when you see on the top right, there says panelists and then attendees. You click the attendees. And then when you hover over
good. I go to attendee, yes.
Now when you hover over them, and you should have allowed to talk as an option.
I see. Good. That is perfect.
Okay.
Thank you.
Sure.
Thank you. It's always good to be a few minutes early, right, Adam? Then you can get this-
Indeed, indeed.
Because every one of these things is a bit different, right? I've used all of them now, about 5 or 6 of these grouping
Sure.
things, and each one of them has different rules, you know.
Oh, absolutely. They're all slightly different, but Zoom seems to be the
Yeah.
common, yeah, at this point.
Okay.
Okay, there's promote.
Here's Radha, yeah. Hi, Radha, good morning. What time is it over there? 7?
Yes, good morning.
Good morning, Radha.
Good morning.
Wow, how do you get all this? See, I have an official background, which is just my office. You get all these fancy ones, all right?
This is actually University of Washington cherry trees.
I know, but how do you get all these beautiful things? I have to get more up to speed with this electronic stuff. Yeah.
I could send you some of the Washington ones.
No, I don't want the Western ones. I'm going to get some local ones. What do you mean? I'm not in Washington right now. I'm in Washington, D.C., not in Washington State. Okay.
I think you would like this one.
Oh, you keep changing them, I see.
Yeah, I actually did hike here. It's called the Wallace Fall.
So if you have so you can change them according to your mood, right? If you're happy or unhappy or something, right?
Most of them are green. And I did hike here too.
Oh, wow, wonderful.
Hurricane Ridge. These are 6,000
Yeah.
feet and above.
Uh-huh.
Yeah.
Have you go up to the crazy mountain yet? No?
No, but I went close to the,
Because you have a mountain there to ski, which is very dangerous, right?
oh yeah, but we went to the third boroughs of the Rainier and heard the sound of the glacier.
Ooh.
Yeah.
Yeah.
But I'll go back to the UW.
Yeah.
Charles, good morning. How are you?
Good, good. I'm doing well.
That's good.
We just trained Charles on the using of the two of the platform.
Oh, very nice, very nice, very nice. John, you saw the note from Martin. He's asking if he's too early.
Oh, the chat, you mean? I didn't watch it.
Yeah.
Okay. I'll answer him.
Okay, you will do that. Okay.
Yeah. But Martin is not a speaker, right?
I don't think so.
Yeah.
Nope.
Good morning.
Good morning.
Oh,
Hi,
good
Rob.
morning to you.
Hi, Rob.
Hello.
Hi. So Adam, you should make Rob a panelist because he's the first person to do the welcoming remarks.
I'm a panelist now. That's been done.
I did that as soon as he entered the room.
Good. Okay. Yeah. I
You
forget
wouldn't
that
see him here otherwise.
I forget that I have to keep flipping between panelists and attendees. Okay. So I was looking at the attendees and I didn't see him. That's why I said what I said. Yeah. Okay. Good. Okay. Rob, you're going to make a presentation or you just going to talk?
Just gonna talk.
Good. Okay. So that makes it easier.
And John, when the student helper arrives, will they be promoting people at that point?
No, I do not. I have not asked the students to do anything like that. The student helper for this morning is, Guan Zhepeng. And he's a student of Guanyang. And I don't see him yet. But that's okay, we can handle it. We have enough people to handle it, right?
Right. No, I was just checking. I'm gonna make everybody co-hosts just so.
Yeah. The thing is, do we see any speakers yet? That's the question.
I do not. I'm keeping a close eye on it.
I don't know. Yeah, it's no. Yeah.
We've got 5 minutes.
Yeah, but there's no academic grace here. We are tight. In these teleconferences, one thing I learned is you don't have any time flexibility. You have to be up to the speed. Okay.
Understood.
But for the session, you have more than 5 minutes. You have 20 minutes because the session is supposed to start at 10:45. Oh, we have one speaker, Taha, is online.
Yeah, hello, good morning.
Hi, good morning. How are you?
Good, how are you?
What time is it over there where you are?
So I'm in Houston, it's 9:26.
Okay, you're okay.
Yeah.
Yeah. I'm worried the people from Australia because it's going to be early morning there. Yeah. Taha is on. Yeah, okay. See, you guys are all coming in with your fancy backdrops. I'm coming with a poor working man office desk, right? I have to learn how to do that. I have some nice ideas about what kind of backdrops I want. Maybe tomorrow I'll try it. When is Halloween actually? Friday?
Saturday, I think.
Saturday. Okay, so we should try to get some jokes about Halloween since it is a security conference, right? It's very appropriate. Okay, people are coming in now. Tansu is on the attendees from Australia. Good.
hi, Patrick. This is Mary Barris. You said that somebody's coming to pick up the check today. Could you please call me back and tell me when? I just want to make sure that somebody's here when they come.
Yeah, 1 minute, Robert.
Thanks, bye.
I mean, I'll start it and then I'll introduce you.
Okay.
Okay, I will start. Hello to everyone, good morning and welcome to GAMESEC 2020, which was supposed to be in beautiful College Park, but we are doing it now virtually for the first time in the history of this conference. I would like to introduce our Dean, Robert Briber, the Dean of the A.J. Clark School of Engineering, for some opening remarks for the conference. Rob, you have the microphone.
Thank you very much, John. I'm very happy to be able to welcome you to the first ever virtual conference on decision and game theory for security, or GAMESEC, hosted by the University of Maryland. It's the 11th year of this prestigious and successful conference. We actually hosted GAMESEC at College Park back in 2011, and a little bit sorry we can't have you on campus this time. Campus has actually changed quite a bit since 2011. It would be nice to have you here. We have a lot of nice new facilities, but maybe we can get you back in the not too distant future. Over the last decade, as all of you know, we've experienced an explosion of information technology products and services. And the era of digitization and networked immersed society is now upon us. As a result, security, trust, and privacy permeate every aspect of life, work, and society. And this applies equally to individuals, families, neighborhoods, organizations, companies, government, factories, offices, healthcare, schools, entertainment, news, dissemination, homes, sports, etc. It's really striking. In fact, I saw a crazy news story the other day about some security researchers who were exploring the security implications of IoT devices, and they actually demonstrated hacking of a IoT connected coffee pot and had the coffee pot ask for ransom in Bitcoin if you wanted your coffee. So that's the kind of extreme that things are going to now. At Maryland, we've realized the critical importance of cybersecurity and created in 2010 the Maryland Cybersecurity Center, an interdisciplinary center of excellence with broad interests and activities in both theory and applications. The Maryland Cybersecurity Center is a joint effort between the A. James Clark School of Engineering and our sister college, the College of Computer, Mathematical, and Natural Sciences. And it brings together faculty with expertise in the core areas of computer science, electrical engineering, but in addition, also those with backgrounds in economics, social sciences, computer, human interaction, and other areas of engineering. And it has particular strengths in cryptography, programming, language, software security, behavioral aspects of security, empirical security, and cybersecurity economics. We also have a new effort in secure chip fabrication as well. And we even have a living learning program for cybersecurity starting at the freshman year with new students. We're also strong participants in the National Cybersecurity Center of Excellence, a public-private partnership established in 2012 by the National Institute of Standards and Technology in partnership with the state of Maryland. This Cybersecurity Center of Excellence is a collaborative hub where industry organizations, government agencies, and academic institutions work together to address the most pressing cybersecurity challenges for business. We've also strengthened our collaborative research and education programs with the NSA, which has designated the University of Maryland as a National Center of Academic Excellence in Information Assurance Research. University of Maryland was named an Intelligence Community Center of Academic Excellence by the Department of Homeland Security. And so we're really, we're actively working in all of these areas. We're discussing new hires in the future. when things smooth out a little bit from this pandemic. I'm really looking forward to some of the presentations and wish you the best of luck with this first ever virtual conference for GAMESEC 2020. Thank you very much. And I'm going to turn it back to John now.
Thank you very much, Rob. Thank you very much for your nice comments. And hopefully we'll stand up to your expectations as far as the conference is concerned. Thank you. Have a great week and a great day. The next person who's going to speak, actually not in person, is our director of the Institute for System Research, Ankur Srivastava, who gave me a video for you to play because he has a conflict. So we'll see how this works. I'm going to try to share my screen now and see if I can go to the video and find it, if I can find it. All right. Should I open it first, I guess, yeah. Let's open it first.
John, I'm not sure why, but I can no longer hear you.
John, we cannot hear you.
John, I think you want to check where your output is going. If you go to the audio and look at where the output is going, it may be through some other channel. Please check that. On the Zoom preferences.
On the little mute button, there's a little caret up arrow. Click that, and then go to audio settings. Or actually up top, it says select a microphone. Make sure that you have the correct one selected, because we can no longer hear you.
If this one is better, can you hear me now?
Yeah.
Yes, now we can.
Yeah.
Thank you.
Okay. What about now? Can you hear me now?
Yes, sir.
Okay, so the flip-flop did it. The usual. Let me see if I can find the screen now that I want to share, because everything went wrong when I tried to go to the video of Ankur. I do not know why, but here it is. Let me see if I can share this. Oh no, that's not it. Okay, it is okay. All right, so let's see if I can play it. Okay. Can you see it?
No, it looks like you shared just the Microsoft Word document. You'll want to share probably your desktop if you're going to be using multiple windows.
Sorry, what should I share?
So hit stop share up top.
Yeah.
Then when you click share again, choose test desktop up top. But then below that, you'll want to click the two check boxes, one that is share computer sound and the other optimize for video.
Okay, yeah.
And then hit share again. And as long as desktop is chosen, you can hit share again and then pull up the video and play it.
Where is the desktop? Is that the big one? If I go to Microsoft and I keep it, you're not going to see it? No?
It only shows, no, it won't show the video that it's linked to. It'll only show the document. So if you choose desktop, it's the very first option.
It will say screen.
Yes.
Okay, fine. And now share the video or so, or click the video.
Yes, but we're getting a lot of,
You getting now? No?
yes.
You see it now?
Good morning, everyone. On
Yes.
behalf of the University of Maryland and the Institute for Systems Research, I would like to welcome you to GAMESEC 2020, the conference on decision and game theory for security. My name is Ankur Srivastava, and I'm the director of the Institute for Systems Research. ISR is a permanent interdisciplinary research unit within the A. James Clark School of Engineering at the University of Maryland. Since our founding with John Barris as the first director in 1985, as one of NSF's original engineering research centers, ISR has been at the forefront of interdisciplinary research and education in the system sciences and systems engineering. Today, we are home to more than 60 faculty and other researchers from 13 departments in 5 colleges across the University of Maryland. ISR develops both basic solution methodologies and tools for systems problems in a variety of different areas. Our basic research has resulted in many algorithms and sophisticated models for decision-making and control, communications, and the computing needed to model and design highly automated, autonomous, and distributed engineering systems. We are proud to be celebrating our 35th year anniversary in 2020. As we all know, cybersecurity is a major challenge in today's connected world, as we are increasingly connected by advances in information and communication technologies. As attackers and attacks become more sophisticated, inevitably we will need to shift to new security paradigms and understand the fundamental trade-offs in the design of secure systems. In my own work, for example, we are investigating how fundamental constructs in hardware and software contribute to system security. The GAMESEC conference will approach issues of cybersecurity from the perspective of game theory, which can capture the competitive and strategic behaviors between an attacker and a defender. Game theory provides a promising baseline framework for analyzing and designing systems security and has already been applied to multiple security domains, including wireless community, cloud computing, industrial control systems, Internet of Things, and national homeland security. This year's 10th GAMESEC conference is a continuing celebration of this success. This is the first GAMESEC conference to be held entirely online, to be held virtually. And UMD is proud to host this important meeting for the second time. We previously hosted it in 2011. Once again, ISR's founding director and UMD's distinguished university professor, John Barris, is one of the 2 general chairs of the conference. He's joined in this role by his former student, Professor Radha Purvendra of University of Washington. I would like to thank both John and Radha for their commitment and work to take GAMESEC virtual this year. I'm sure you will find the next 5 days to be enlightening and engaging. Once again, welcome to GAMESEC.
Thank you. And thanks to Ankur, and thanks to Rob, and thanks to the University of Maryland, the Institute, for their support. Just before we start, I want to emphasize to everybody that time is important. And you saw what happens in my attempts to try to get online. So we should all try to keep our presentations to whatever the chair of each session tells us, and the questions and answers. And with that, I will turn over the control of the session to Charles Kamua for the first session. Thank you all very much, and welcome to the University of Maryland.
Yes, thank you, John. Thank you. You know, it's my honor to be sharing this session. And the session, as you know, is on machine learning application to cybersecurity, a growing research area. We do have 5 papers in this session, and I have already identified the first 4 speakers. I suppose the last one is not yet online, but the talk will be like after 12, you know. So without taking much time, you know, so one thing to emphasize, 20 minutes for every talk. I'm gonna put a timer. I have a timer here with me. And nobody should be going above the 20 minutes. After the talk, there will be an opportunity to answer a couple of questions. That will take another 5 minutes, you know. So with that said, I would like Mark to start the first talk.
Hello, everyone. I hope that I'm coming through okay. Right. Okay.
Yes, we can see.
That's fantastic to hear. Thank you. Okay. Hello, everyone. My name is Mark Katzef. I am a PhD student at the University of Melbourne under the supervision of Andrew Cullen, Tansu Alpcan, Christopher Leckie, and in collaboration with Justin Kopacz from Northrop Grumman Corporation. My presentation today will be discussing distributed generative adversarial networks for anomaly detection. Without further ado, I'd like to begin my presentation. Throughout this presentation, I'll be giving an introduction to collaborative anomaly detection. I'll be discussing generative adversarial networks. I'll be discussing PureGAN, which is a novel combination of generative adversarial network components that has been designed for collaborative anomaly detection, before summarizing things with a conclusion and future work. So first off, collaborative anomaly detection. The task of anomaly detection is identifying outlying samples from some training set. Anomaly detection is typically performed centrally at a single server. All state-of-the-art anomaly detection methods process an entire data set in a centralized position. This ignores some of the benefits that are available in distributed computing platforms, such as the cognitive radio network. These benefits of distributed computing platforms are increased robustness to device failure and diversity in available data. Our research is focusing on the use of cognitive radio networks for collaborative spectrum sensing and data processing, with a particular aim on network security. Wireless network security requires knowledge of peers, adversaries, and typical network activity. Shown right are example plots of the type of data that cognitive radio networks are able to obtain. This is easily obtained data such as transmission duration, payload size, and packet inter-arrival times. Even with this easily obtained information, we are able to see distinct visual differences between typical activity, shown left, and anomalous activity, shown right. It is the task of an anomaly detection model to identify the differences between typical activity and anomalous activity. As I stated previously, these models for identifying anomalous activity are typically built in a centralized manner. However, moving this processing to the network's edge would reduce communication, which would be ordinarily required to develop these central data sets by collecting the data by bringing together the data that cognitive radio devices collect in a distributed way. This processing at the edge of the network is also able to avoid any single points of failure. The typical method for processing this data in a central way is by using deep learning models. These have been very popular in recent years. By now, we would have all seen this type of architecture diagram shown right. A deep learning model is able to approximate arbitrary functions through a series of simple steps, here shown as multiple layers of individual nodes, each node taking a weighted sum of previous layer outputs, applying some nonlinear activation function before passing this information to following nodes. Through these simple steps, the deep learning model is able to approximate arbitrary functions and has been shown to achieve strong performance in tasks such as classification and, as I will describe later, generating data as well. These are two important tasks for the network architecture referred to as the generative adversarial network. These will be important roles in the task of anomaly detection that I'll discuss at later stages in this talk. Right now, I would like to just bring your attention to the fact that these deep learning models are able to be distributed by a combination of sharing data parameters, by sharing parameters, or by sharing training gradients. Sharing these parameters in this way is able to reduce the computational and communication cost for participating devices, or to access some useful deep learning model for the purpose of anomaly detection. With these pieces of information in mind, the key contributions of this work are a game theoretic evaluation and interpretation of a GAN that we have referred to as peer GAN, as well as a distributed formulation of peer GAN, focusing on its use in anomaly detection. So I've now referred to GANs many times in this introduction. It's finally time to explain what this architecture is made up of. The GAN was introduced in 2014 as this structure of two neural networks, generator and discriminator. These two networks are given complementary tasks, where the discriminator has a classification-like task where it is expected to tell the difference between two possible inputs: the output of the generator or samples drawn from the training data set. The discriminator, being a deep learning network, is able to perform this classification task with high accuracy. It is able to accurately tell apart the generator and training output until the generator is trained appropriately. The generator is trained against the discriminator in a game, as I will discuss in the next slide, such that the generator maps samples from an arbitrary distribution of noise to signals that could have realistically been drawn from the training data set. After successful GAN training, you have produced a generative model that is able to produce realistic looking signal samples. This generative model is a valuable tool for anomaly detection in that it is a representation of all of the samples that are present in the training data set. It is a compressed representation of the type of activity that might have already been given during the training step. As said previously, this interaction is best described as a non-cooperative game between the player's generator and discriminator. In particular, it is a min-max game where the players are parametric functions. As I mentioned earlier, they are deep learning models. These parametric functions draw their parameters from each of the player's action spaces, shown here as capital theta G and theta D. Each of these players is tasked with maximizing their own utility function, shown as UG and UD. As I stated earlier, this is in fact a min-max game where UD is equal to negative UG, and both of these are based on the Jensen-Shannon divergence between the generator's learned distribution and the training data's distribution. The discriminator's task is to drive these distributions as far apart as possible, telling apart the generator's distribution from the training data distribution. The generator's task is the reverse of that, driving the two distributions as close to each other as possible, where the generator results as an accurate representation of the total training data. Since their introduction, GANs have sparked research to the extent there are now over 500 different GAN variants on online repositories such as the GAN Zoo. Each of these variants addresses different shortcoming of the GAN, busy focusing on different models such as different model types, model connections, or different loss functions which use different distribution comparison methods, or adding some additional terms. 4 GAN variants are highlighted here. These have played an important role with the peer GAN. The modifications that these highlighted GANs make are to the distribution comparison method, shown here as non-saturating GAN and WGAN being 2 prominent variants of the GAN. The non-saturating GAN is able to achieve higher generator output fidelity by minimizing the Jensen-Shannon divergence. However, it is shown to occasionally result in a generator that outputs only a subset of the overall training data distribution. The Wasserstein distance GAN is a variant that focuses on representing a wider variety of the training samples. Together, these two loss functions can be combined to achieve a generator that more accurately represents a wide variety of samples of the training data set. The remaining two highlighted components work in tandem to provide us an essential feature for efficient anomaly detection. The bidirectional GAN and the conditional entropy, also known as ALICE by GAN, are able to provide an additional mapping, which I will address in subsequent slides. With all these components, I can now present the peer GAN, which is a novel GAN for collaborative anomaly detection. The peer GAN uses the components that I referred to in the GAN variant slide to arrive at a structure shown here. This structure moves away from the original GAN formulation by introducing an encoder and a regularization term, which is the reconstruction error or reconstruction loss when passing a sample through the encoder and generator. Temporarily ignoring the discriminator, we have the components of an autoencoder, which is a popular neural network, a popular machine learning model these used for anomaly detection as well. Passing a sample through the encoder and generator, we are able to arrive back at the original sample or an approximation of it. Comparing such approximation with the original sample is one method of performing anomaly detection. I will get back to this, but using an autoencoder alone has some significant drawbacks for anomaly detection in that the autoencoders are unable to reconstruct samples with the same fidelity as a GAN. By introducing this discriminator, which is, as I've previously stated, a deep learning model that is accurately able to tell apart two distributions, the generator is forced to produce samples that more accurately represent individual samples of the training set. But taking a step back, this structure needs some explanation. Instead of just pitting a generator and discriminator against each other, this peer GAN introduces this encoder, and the two distributions that are presented to the discriminator are the output of the generator and output of encoder. As in the original GAN, this plays out as a game where the discriminator is tasked with telling apart these two possible inputs. It needs to tell apart generator output from encoder output, while the encoder and generator are tasked with minimizing this difference by producing the data that they have not got access to locally. So if generator has access to a noise vector, must produce a corresponding sample. The encoder has access to a sample and must produce a corresponding noise vector. This is all represented by this loss function, this utility function shown below. The discriminator is tasked with maximizing the sum of Jensen-Shannon divergence and Wasserstein distance between these distributions, while the encoder and generator are tasked with minimizing this distance. One important feature of this, by exposing the discriminator to both mappings learned, or both of the mappings learned in this, the mapping learned by generator and encoder, the discriminator acts as a summary of the learned mappings from both of these competing models in this network. This discriminator acts as a compressed representation of the learned mappings, which allows for an effective collaboration scheme as depicted here. A significant benefit of the peer GAN is that multiple instances may be produced on separate devices and trained on local data. And by exchanging only the discriminator parameters at regular intervals, these separate instances of the peer GAN are able to benefit from the learned mappings of neighboring devices. With these discriminators acting as a summary of the learned mapping from the generator and encoder, when a device receives a neighbor's discriminator and trains locally against this discriminator, their local generator and encoder are encouraged to learn a compatible mapping with the neighbors, which is able to fill in gaps in the locally learned mappings. Training in this way avoids any transmission of data samples, which for large data sets is able to significantly reduce the communication cost. This table shows a brief overview of the communication required for a centralized or distributed approach that results in each of the participating devices with a trained model on the entire dataset. So in the centralized case, each device is required to transmit its local data to some central server for processing and receives a total of p parameters of the centrally trained model. For the distributed case, we do not transmit the entire data set of each of the devices. We instead transmit the model parameters at regular intervals. So the communication cost shifts from being linear in terms of the data set size to being linear in terms of the model size. As I stated before, for large data sets, this can be a significant decrease in communication. When it comes to training the pure GAN, the expected trends are followed. I have overlaid the expected losses or utility values for each of the models in the pure GAN are overlaid in the top portion of each figure here. Presented here is a centralized pure GAN training outcome and distributed pure GAN training outcome. For centralized pure GAN, we see that the encoder, generator, and discriminator losses approach the expected values after a brief period of what looks like after a brief spike in their utility functions, or loss functions, which are the negative of utility. But we see that as training progresses, the generator and encoder learn appropriate mappings that are able to confuse the discriminator where it is no longer able to discern between the two distributions. The same is true for the distributed pure GAN, where we have, so in the centralized pure GAN, I should clarify, we have trained a single instance of pure GAN on the entire data set on one device. In the distributed pure GAN, we have instantiated 3 separate pure GANs on 3 separate devices, and these separate instances exchange their discriminator parameters at regular intervals to perform collaborative pure GAN training. We see in both cases that the expected losses are achieved in the long run with some slight oscillation in the distributed case as a result of the local models updating to accommodate this recently received discriminator parameter set. Throughout training, we see that the training gradients decreased to 0 for the generator and encoder, showing that they are no longer able to improve their performance against the discriminator, and that they have filled in local gaps in their learned mapping. The result of this training is a generative model, which is the combination of encoder and generator allows us to reconstruct samples. Reconstructions are shown in these charts as gray overlays. Charts on the left show typical samples being reconstructed. Charts on the right show anomalous samples being reconstructed. We can see that for typical samples, the samples that the pure GAN has been exposed to throughout training, reconstruction occurs with a much higher accuracy. The error between the reconstruction and the typical sample is lower, showing that we have accurately represented the typical data set samples. Using this reconstruction error, we are able to arrive at some anomaly score. Samples that have a larger reconstruction error, like those shown in the anomalous samples right, are considered anomalies, given that their anomaly score lands above a threshold. Using this reconstruction error as an anomaly score, the pure GAN is able to achieve commanding anomaly detection performance, as shown in these far right columns here, with centralized pure GAN and distributed pure GAN achieving comparable or better performance than state-of-the-art methods that are also based on reconstruction error. Here we see autoencoder's performance. So the structure of the autoencoder alone is in some cases able to outperform the pure GAN, but across the 4 data sets that we have tested on here, the pure GAN is the only one that achieves consistently high performance where some more testing data sets, such as the synthetic data set that uses differences in noise levels as the anomaly, only the peer GAN is able to perform successfully. The remaining methods achieve no better performance than randomly guessing and achieve OROX of 0.5, which is the result of being confident about none of their predictions. So in conclusion, our findings with the peer GAN are that it is able to rival state-of-the-art anomaly detection methods, which are suitable for cognitive radio networks, while avoiding a single point of failure and reducing communication costs. Moving forward, the intention is to evaluate peer GAN on additional networks with more devices and expose peer GAN to training in different environments that may contain anomalies, which would make the training process more difficult, and train the related network type, which is the adversarial autoencoder for collaborative anomaly detection. Thank you for listening to this presentation. I'll now take any questions. Please, not all at once.
Hi, Mark. Thanks. This is John Barras. Thanks for a very nice presentation. I had a question which I put on the chat. Basically, is the following: in many of these problems of anomaly detection, usually we don't have large data sets to train. So, can you say anything about the size of data set you need to get good performance with the methods you described? This is important because in anomaly detection, usually we cannot assume that we're going to have large repeats of the same anomaly detection, especially if they're malicious anomalies.
Right. So one of the benefits of the problem that we're focusing on here that considers network security, the cognitive radios here are collecting data in real time. This can be used to expand data sets indefinitely. This would, well, it would encounter problems with storage at each of the local devices. We haven't experimented with online training, but that would be an option moving forward. We have considered that anomalous activity throughout training can significantly impact the resulting models. We are yet to experiment to see, we haven't pushed it to its limits yet to see how tolerant these models are. So just regarding the dataset size itself, we have experimented on datasets that span several orders of magnitude of the number of data samples. For this, for our CRN dataset, we have several thousand samples, whereas the KDD dataset has tens of thousands. So actually, sorry, the CRN dataset, it's less than 2,000 samples. And we have achieved some promising performance spanning these different dataset sizes.
Mm-hmm. Thank you.
Thank you for the question.
Any other questions? Okay, Mark, thank you very much. And let's go to the next speaker. The next speaker is Ryan Shee, and I can see him, so you can share your screen.
Oh,
yeah, we can hear you. Yeah.
Can you hear me now?
Yeah, just share your screen.
Yeah. Sorry, I think I just upgraded my system. I might have to log out of Zoom to be able to share my screen. It's some permission issue. I'm sorry about that.
Okay.
right. Can people see my screen now?
Yes, we can see you. Go on. Thank you.
All right. Sorry about the technical glitches.
No problem.
So, okay, so hello everyone. My name is Ryan Shi, and I'm a PhD student at Carnegie Mellon University, working with Dr. Fei Fan. It's my great honor to be here today, and for today's talk, I would like to introduce our work on learning and planning in feature deception games. So this is a joint work with Ariel, now at Harvard, Sridhar at Perspective Labs, and Kevin, Noam, Nandi, and Charles at the Army Research Lab. So let me get started. So deception in cybersecurity setting is a very intuitive idea. So let's say we have a network with a bunch of servers, and each of these servers has a lot of specs, which we will call them features throughout this talk. And these features can be, for example, the operating system, the type of the web server, or whether a particular port is open or closed. So we'll get to what these features can be in a minute in more details. But for now, the point is, a cyber attacker has many tools to probe these feature information. So this information can be valuable to the attacker because the attacker can figure out which node is valuable or which node is vulnerable, so on and so forth. So deception now comes into play if we can give the attacker false information when they scan the network. Like you can see on the figure here, the orange blocks are what we call the true features. So that is, they are the services or properties that are actually running on the server. And then there are green blocks, what we call observed features. And these are the deceptive information that we as a network administrator choose to give to the attacker. So this can potentially be very useful because, if you look at the slides, and just using a very toy example here. So suppose like this node 2 here is actually very vulnerable. It's actually very valuable to the attacker, but we somehow show another set of features, and so that the attacker thinks it's not so valuable, and then the attacker might actually not choose to attack it. And so in this way, we can actually exhaust the attacker's effort in a relatively harmless way. So here's a bit more about the features that we just mentioned. This is probably an incomplete list of features that we might care about, or more precisely, the attacker might care about. So we have the operating system, or the server's IP address, or what ports are open or closed, and service, the version of different services running on the server, and also some continuous features like the latency or like the rate of background traffic and so on. So, but the thing is, as I mentioned earlier, what feature configurations are valuable to the attacker and what are not. So let's make it more precise by introducing the attacker's behavior model. We consider in this work a very broad class of bounded rationality behavior models for the attacker, which is characterized by a score function f. So the score function takes the observed feature of a target as input, and then it spits out a non-negative number, which is the score of this target. The higher the score, the more valuable the attackers think this node is to attack. Then we assume that the attacker will choose a node to attack with probability that's proportional to the score he gave them. So in our model, we in practice, we will use a neural network as a general function approximator. And if we knew the score function perfectly, then we can compute an optimal defender strategy, assuming the particular adversary's behavior model. But of course, like in practice, we don't know what the attacker score function is, so we have to learn it from data. And that brings me to the main contribution of our work. We provide a learning and planning pipeline with end-to-end theoretical guarantees. So first of all, we characterize the sample complexity of learning a good score function, and then using the learning score function, we provide an approximation algorithm which computes the optimal feature configuration. And let me introduce both of them step by step. So first, let's focus on the learning part. To learn a good score function, of course, we need data, and I'm gonna elaborate on what a data point looks like in our model. So here, a data point consists of 3 parts. first there's a network, and which has a bunch of nodes, and each node has some features, and the features of each node will be part of the data set. And of course, we also need the label of the data point, which is the node that's actually being attacked by the attacker at that round of interaction. So, and as you might probably see here, so each of our data point can actually have different sizes, meaning that we don't really have to always collect data on the same network always, which might be useful in practice. And during learning, like the objective naturally is just to maximize the likelihood of observing the attacker's behavior. And if we assume a very simple form of score function like a one-layer neural network, then the log likelihood function is concave and we can solve it exactly and efficiently. But for more complex score functions, of course, we are not guaranteed to get a convex problem, but we can always use gradient descent-based methods to get a reasonably good learning result. And let's look at some theoretical results here. So for the relatively simple score function like a neural network with one hidden layer, we are able to show that for a feature deception problem with m number of features, we only need to collect attack data points based on also m different feature configurations only. So this is a very modest requirement, because a feature configuration is basically the collection of all the features of all the nodes in the network. So as long as one of these features are different, then they are considered different feature configurations. So we only need to collect data on a linear number of them. And for each of them, we need a polynomial number of data points so that approximate the score function within arbitrary precision. And we also consider a more advanced case where, if the attacker is aware that we are using these historical data to learn their behavior model, then the attacker might occasionally want to confuse us by not attacking according to their behavior model. So our second result concerns the robustness of our learning algorithm against data poisoning attacks. So we are able to show that if the attacker deviates from their behavior model on a small portion of the data, then we are still guaranteed to learn a reasonably good behavior model. So that's about the learning part. But of course, the end goal here is not just to learn the behavior model. We want to design the optimal defender strategy. But before we go there, the thing is, if we had known the perfect score function, then of course we can compute an optimal defender strategy. But because we are learning it, we are almost always not gonna learn a perfect score function. Then what would happen if we are saying we have to plan against only an approximately good behavior model? Are we still guaranteed to get a reasonably good defender strategy after all? And here we answer this question affirmatively. Basically, this theorem is saying that as long as we have reasonably good, even if not accurate, score function as a behavior model, and we are still guaranteed to get a approximately optimal defender strategy in the end. So that's kind of the theoretical backbone of why we are justified to do this two-stage learning and planning pipeline. And now I'm going to the planning part. So let's say we have some score function that we have already learned, and we want to set the observed features in an optimal way. So setting the observed features basically is equivalent to the defender strategy in this case. So this is an optimization problem under feasibility and budget constraints. So the objective here, of course, is to minimize the defender's expected loss. So for feasibility constraints, we are basically saying that, in some cases, for a particular server, we cannot make it appear to the attacker in arbitrary ways. There are some rules that we have to follow. Otherwise, the system will look very incredible to the attacker, and then the whole idea of deception will just fall apart. And the budget constraint is also quite intuitive. That's subject to, in some cases, it's like the system capability, and in other cases, it's like human resources constraint on how different we can set the observed features from the true features. So that's the optimization problem. This problem, of course, is not convex, and it's actually NP hard to solve, even if there is only a single binary feature. So although it's NP hard to solve, we can still try to use different heuristics to find a good solution in practice. And here we formulate a mixed integer linear program to find an approximate solution where we are able to show that this mixed integer linear program will give you a 2 epsilon square approximation, an additive approximation. And we can actually, the milk I'm showing here is will run not very efficiently because of the fraction in the optimization objective, but we are able to further speed up it by using some binary search on the objective function. So here we show some experiments on our algorithms. And the first one on the top left, the graph there is basically showing our learning results. Here we plot the learning error against the size of our data set. So as you can see, like intuitively, when you have a larger data set, your learning error will decrease. And actually, in this case, we don't need a large data set to achieve a reasonably good learning error. Like you can see here, it's about like with 2,000 data points, we can reduce the attacker's probability error, which is modeled as the total variation distance between the attacker's distributions. We can minimize that error to like 0.1 roughly. And then if you look at the bottom left figure, where we show the results on the planning. So in the planning part, like we already know that our algorithm will give an approximately optimal solution. Then what we care about here is the efficiency, is the computational, like the running time of the algorithm. So we can see that with the binary search enhanced mixed integer linear program, we are able to handle problem instances which have like 200 targets within roughly 1 minute or so. So this shows that our algorithm is able to handle a lot of like real world problem sizes at a reasonable running time. And of course, like on the right, we show this on the experiments which consider both learning and planning. So here, what we are looking after is the solution gap, because we are not learning a fully accurate behavior model. Then we really care about in the end what's the solution, the solution quality guarantee. And here we see that in the top figure, we also see like when you have more data, and reasonably your solution gap will decrease. And also if you have the problem size becomes larger, your problem also becomes slightly harder to solve. But in all these cases, we can still make the solution gap that's smaller than basically 10% in all these figures. And so that's kind of the experiments that basically trying to validate our algorithms. But I would like to end today's talk with another set of experiments. So I want to come back to our original idea of deception. So I'm going to show a case study, and using this case study, we are really trying to show, why deception is useful and how our algorithm use deception strategies which are reasonable in real world, and how our algorithm is able to handle an attacker who doesn't really follow the very form of support function that we already assumed in the beginning. So here, let's think of a credit bureau's network, and the network has 10 nodes. And it's a very toy example, but the point here is no longer to show the scalability. It's more to show why our algorithm is reasonable here. So let's say we have 10 nodes, and then we have some mail server, your web server, or a database server, and so on. So there are six binary features as you see on the slides. So each node, according to their type, will have different features. And some node would incur a high loss if being attacked, because like the database servers, and some other nodes will have a relatively lower cost of being attacked. some database servers might even have access to more information than others. So the loss of, even for the same database servers, their loss can be different. And of course, like on the defender side, there's a cost of changing the features from the true features to some fake observed features. And that's basically the setting of this problem. And then we are going to introduce our attacker's behavior model here. So in this case study, we are not going to use the attacker's behavior model we assumed earlier. It's not a score function anymore. Instead, we assume a behavior model that's common in security analysis, where the attacker cares about a subset of features. And we call these features a requirement. And the attack is uniformly randomized over all the targets that satisfy the most number of requirements. Although this decision rule, it doesn't fit into any of our previously assumed score function. We can approximate it by basically giving huge weights to the required features and 0 weights to the others. So let's first consider an APT type of attacker who had expertise in Linux and wants to like exploit the SMTP service. So here the decision rule is based on these three features, and without deception, what the attacker would do is that they will just attack uniformly, randomly among the nodes from 5 to 9, each with probability 20%. But now let's see what our algorithm does. So in this solution, we see that the solution is shown on the bottom right here. So in the solution, the algorithm actually makes node 1 to appear very attractive to the attacker, to the extent that the attacker now only randomized from among nodes 1, 5, 6, and 7. So what does that mean? Like that basically saying that we are pushing the least harmful target to the defender into the attack set for the attacker and pull out the most harmful ones out of the attack set. That basically reduces the defender's expected losses and compared to not using deception at all. So this is, I have to say that this is the solution that we get from the whole learning and planning pipeline. So the attacker's behavior model we described earlier, that is the ground truth, but our algorithm didn't know that, and we make it learn that from data. So I'm gonna show the last set of case study, which is, let's consider another type of attacker, which is a botnet attacker who wants to create a bot by exploiting, say, the NetBIOS service. And let's say they have some expertise in Windows. So their decision rule now is based on 2 requirements, Windows operating system and NetBIOS. So that means they will attack nodes 0, 1, 3, and 4 here, each with probability 1/4. And let's see what the algorithm does. So in the solution here, the algorithm basically shuts down the NetBIOS on nodes 3 and 4. That means that the attacker will now no longer consider nodes 3 and 4 in the attack set. They will only consider node 0 and 1. So because why the algorithm is doing this is because nodes 3 and 4 have relatively higher loss compared to the other 2 nodes here. So the algorithm wants to pull these 2 nodes out of the attack set. And that basically effectively reduces the defender's loss from 0.2 to 0.1. So so that's kind of, with these 2 examples, I'm trying to give you an idea of why these deception strategies make sense in practice. And of course, the real world examples will be much more complicated than that. And I'm happy to also take any questions regarding like all sorts of different design considerations of this model. But that is my final slide. And I would like to thank you for your attention, and also thank all the organizers for this great first virtual GameSec conference. And that's it. Thank you.
Yes, thank you, Ryan. Thank you for the nice presentation. We have 2 questions. The first one by Juntao. You can answer your question, please.
Hi, Ryan. Thanks for the exciting presentation. Yeah, everyone can hear me, right? Yeah. Could you comment a bit on the information structure on this deception game? Usually the attacker may not have the complete information of this deception game because the defender wants to design a mechanism in order to trap this attacker by attacking these false valuable servers as usual in the graph. And maybe you can just comment a bit about this the information structure of this deception gain. Thank you.
Sure. Yeah. So we are making the assumption that the attacker will not observe the true features, but the attacker will always observe all the observed features. So this assumption, of course, there's also some flexibility in that. First of all, you might think for some attackers, maybe they are so advanced that we as defender cannot trick them to believe in a particular observed feature. And if we as a defender, we already knows that, then we can set the feasible region of the observed features to be like a singleton, which is the original feature, so that we as a defender, we consciously know that we cannot trick them into this. But of course, I think the limitation of this current model is that when the defender is not aware of some attackers' more advanced cognitive knowledge about this system, then it would be a bit hard, and that's actually our next further direction on down the line.
Oh, great, thank you.
Yes, thank you, Ryan. The second question is from John.
Hi,
John,
Ryan.
you can answer.
Yes, hi, Ryan. Very nice talk. So, what can you say about the minimal accuracy by which you need to approximate the score function and still get good planning results? And a sequel question is, can you do without trying to get a functional approximation of the score function, just working with the samples directly?
Yeah, all right. Yeah, thank you for your question. So I think to answer the first question, we are able to show some, let me see if I can go back to that slide. Yes, so here, basically what we are saying is, if we can approximate the score function within some multiplicative error that needs to be smaller than a quarter, but it can go arbitrarily small, then we can show that our final solution, the defender's utility solution, will be small.
Okay, thank you. Yeah.
And for the second question, I'm actually not completely sure about if there's another way to go about using the data without a functional approximation. But I would really like to have a further discussion offline if you'd like.
Okay, thank you.
Thank you so much.
Yes, thank you, John. The last question will be from Pavli Agrawal. Pavli, answer your question.
Hi, Ryan. Thank you for so my question is a little bit on validation part. What do you expect if you have, instead of an algorithm, human attackers? How do you think that your results will deviate, or what do you expect with human attackers?
Yeah, indeed. That's a great question. So there are two things that I would like to bring up. First thing is this particular score function behavior model that I used in the work. That's actually based on some comparison with the existing literature on the comparison of like attacker behavior models. That I think that this is like basically following some subjective utility kernel response model type of that, and which has been shown in some previous work that it's kind of the best model to capture the attacker's behavior. And of course, in practice, we do believe that it's reasonable to expect humans to deviate from this very rigid behavior model. And we would like to see how we would actually like to do some human experiments like by engaging with some fake attackers in some human subject experiments to see how they deviate from that. But the general idea there is, in some sense, this deviation can also be captured by a data poisoning attack. Although the motivations are different, but the end results might be similar in that case.
Okay. Yeah. Thank you so much.
Thank you.
Yeah.
Yes, thank you. Thank you, Han. Thank you for the great presentation. We're gonna go to the next speaker, Alonso. If you can share with us your slides.
Yeah, let me just do it. Mm,
Yes, great. So you can start now. Your 20-minute start.
all right, thank you. So hello everybody, my name is Alonso Granados and I am a PhD student at the University of Arizona. And this work was done with my previous advisor in the University of Texas El Paso as an undergrad, Christopher Kickenbell. So I'll present our work in a realistic approach for network traffic obfuscation using adversarial machine learning. So first, I'll talk about some of the current network vulnerabilities that we have. So despite the encryption techniques that we currently have, the encrypted network traffic can still have observable characteristics. And in particular, these characteristics are exploitable. And for example, these characteristics can be the packet sizes or the inter-arrival time of these packets between the server to the client. So an adversary can accurately classify the encrypted traffic based on these statistical features. For example, they could predict what type of protocol is being used just on what is a packet size that is being sent. So therefore, we're interested in finding a technique to obfuscate the network at this metadata level. So I'll just give like a small presentation of what is the setting that we have. So as I mentioned, we have a server and a client, and we are sending these encrypted packets. So of course, the adversary cannot see the content inside the packets. But even if that's the case, the adversary can observe the packet size that is being sent. And then just based on this information, they can accurately predict what is being sent, what type of traffic flow we are seeing. So adversarial machine learning provides a useful toolbox for this type of problem. And so let's define just a bit of what is a setup in an AML. So we have a classifier model, and it classifies X. The classification of X is given by CX. And the true class of X is given by C star of X. So then the goal of the adversarial learning algorithm is to find a perturbation delta, such that when it is added into X, the true class of X is going to be different from the classification of X plus this small perturbation. And in general, we search for a delta that has a small norm. And the goal of this is that we are interested in that the difference between the original sample and the perturbated sample is imperceptible. So in particular, this approach has been very successful in the imagery field. So for example, in this work by Sexity, we have an image of a panda, and then after adding a small perturbation, we get an image that looks exactly the same for a human, but still the model will classify it with a given, will classify as a given, and you will have a very high confidence that it's making the right choice. So this motivates our approach of doing the same thing, but for the traffic distribution of the metadata features that I'll go a little bit more in depth later. And so we have the same approach. We have the observable features for the adversary, and we want to add a small perturbation to these features. So then the adversary will make incorrect classifications. So our adversary defender model is that we have a defender D who tries to protect the network from an adversary alpha. And then the goal of alpha is to observe this network and classify its traffic flow tau by using this statistical analysis that I mentioned before of looking at these features. And then the goal of D is to disguise tau by changing those features. And one assumption that we have is that D knows the attacker model F. And the reason this is possible is that it has been shown in previous work that adversarial examples are transferable in adversarial machine learning. So we can train our own attacker model, our own model, and then try to fool that model using adversarial learning, and then just transfer these adversarial examples. And they're going to also be adversarial examples for others models, in particular the attacker model. So now the data set that we use is the Internet Traffic Network dataset, which was generated in a research facility by looking at the traffic flow from 1,000 users and during a TCP connection. And this is just a classification task. And in particular, for all the features that they have in the dataset, we only look at the packet size features. And in particular, we only look at the 5 percentiles of these packet sizes. So these 5 percentiles define a distribution over the packet sizes seen during an instance or a sample. And we have for both directions, from the client to server and the server to client. So this is giving us a total of 10 features. So then our goal is to, by just modifying these 10 features, we want to fool the attacker. So we train a classification model that is going to represent the adversary model using a neural network. And in particular, for the imbalance, we did randomly sample of the training set. So we have a equal number of samples when we were training. And this is the accuracy that we achieved in a test set that we also sample. So now I'll present our approach, and just to remind everyone, so what we're playing is we're playing the defender role. So our goal is to create this attack for the adversary. And finally, our goal will be to fool the attacker. And a characteristic of our attack is that we plan to have 2 constraints for the distributions that we have. So as I showed before, we have we're dealing with percentiles. So we have to keep this monotonic non-decreasing property of the distribution and the output of the adversarial examples that we ended up creating. And then a second constraint that we add is to not reduce the packet size. And we have 2 reasons for this. The first one is that if we are dealing with packets, we have the possibility of adding dummy information into the packets, and this will increase the packet size. So we can do this operation easily, but we cannot reduce the packet size because we will lose content of the information. And the second reason is that because we're dealing with a percentile distribution, we could try to generate smaller packets, and this will in fact reduce the packet size distribution. But the problem with this is that it will increase the network overhead. So with this work, we show that by just increasing the packet size, we can create very good adversarial examples without having to compromise the network overhead. So first, I'll deal with the packet size constraint. And the way we did this is that, so the final goal that we have is to minimize a norm between the original sample and then the generated sample. And then the plan is that this is going to have a different class from the original. So what we do is that we clamp the perturbation during this learning process, during this optimization. By clamping it, we don't allow any negative values to be added into the original example. And in particular, we do this during the learning process. And this gives us an advantage because then the algorithm will also optimize for this constraint. And then for the second constraint, the distribution constraint, what we do is that we define this operation on a batch. So we have 2 columns that represent consecutive features in the distribution space. For example, it will be like 25 percentile and 50 percentile. So they're part of the same distribution. And then we apply the following operation to these columns. So what we do is that we subtract them, and then we apply a ReLU function or a max 0 function. And the idea of doing this is that if the first feature is smaller from the second feature, the resultant of this operation is going to be just a 0 value. And in the other hand, if if the first feature is smaller from the second feature, then this will result in a 0 value. And if the other case where we have a percentile smaller but has a larger value than the sequent percentile, we will take that difference And what we do is that we add this resulting operation into the second column. And this will result in, for the features where we have that it satisfies the condition, it will just be an addition of 0. And for the features that the difference is invalid, we will just equalize both features. And then we apply this operation sequentially to make sure that the whole distribution is valid. So now I will present our framework. So what I mentioned before were just 2 constraints that we define and we put into a learning process. So all of these constraints can be applied to any type of adversarial machine learning algorithm. And in particular for this work, what we did is that we implemented this for the Carlini-Wagner attack for the norms L2 and L infinity. And a second thing we do in our work is that we compare it to the previous approach in bare metal, in which they apply the Carlini-Wagner L2 attack. And then after applying it, they did a post-processing to generate a non-decreasing distribution. And something to add is that they did not consider to have a perturbation that is negative. So they allowed to reduce the packet sizes. So we will also see that even with those conditions, our attack has a higher accuracy. So let's start with the attack accuracy. And in this case, we are comparing the success rate per class, which is so this thing defines from the sets of samples that we have for each class, from what percentage we're capable of finding in a successful adversarial example. So pretty much what this means is that the higher the score, the better. So for both the Carlini-Wagner L2 and the L infinity without no constraints, they get 100% accuracy. And this makes sense because they have a lot of freedom to modify the distributions. And then we see that with our approach, RTDA, we get very close to the performance in a Carlini-Wagner, even using the constraints that I mentioned before. And even if our approach is using a stronger constraint, which is that we don't allow to reduce the original sample, we still outperform the previous approach of post-processing the Carlini-Wagner attack. And one of the reasons for this is that after post-processing is applied to a perturbation, we don't have any assurance that this is going to continue being an adversarial example. And this is even more the case when we have very small perturbations that create these adversarial examples, because after the post-processing, those values will be lost and then we'll probably be losing the adversarial. So this is the advantage of putting the constraints directly into the adversarial learning. And then a second part to discuss is how realistic are the resultant adversarial examples. So in this case, I'm showing just a sample of the percentiles for a specific one. And so first, we can see what is, also we have the original, that is just the blue line. And then we can observe what happens when we apply the Carlini-Wagner without no constraints. So to start, we see that in the percentile 0, we reduce it to a negative number, which is clearly invalid. And a second operation that is done in the percentile 100 is that it reduces it does a packet reduction from the original value, which both operations are invalid. And then a second thing is that even after doing post-processing, you can see that the percentile 0 is of size 0, which is also invalid. And again, they do allow to reduce the packet, so we still again reduce the original distribution. And then with our approach, the only thing that happens for this case is that we only increase a percentile 50. And just by increasing this percentile, we're capable of producing an adversarial example. So what this means is that our approach, we show that it creates from all the examples, we're capable of creating valid perturbation and valid distribution adversarials, in contrast with the previous approach that only deal with the distribution part. And then, of course, when we don't apply any constraints, they just don't create, for the most part, never a valid distribution and a valid perturbation. And then we also analyze what was the size of the perturbation, because this will translate directly into how much do we have to increase the packets. So, and this will be the cost that will be imposed into the network. And as you we predicted that our norm will be higher because we're adding stronger constraints into our problem. But we show that the actual mean of the size of the perturbation in bytes, it was smaller. So this was a surprise to us. And then, so that's for the results that we have. And for future works, our plans currently are to test this approach directly into a real network or into a network simulation, and then see if we're capable to design this, to apply this algorithm directly and see what are the results that we get in a real world setting. And a second goal that we have is we plan to see this same problem as in a game theoretical setting where we have a defender and an adversary, and the defender can change the features with a variable cost, and its final goal is just to fool the adversary. So that's everything for my presentation. Thank you for your attention. Cannot see the messages now.
Oh, yes. Sorry, I was muted. Sorry. So thank you again, Alonso, for your presentation. Yes, we have a question online. John, please answer your question. Ask your question directly.
Yeah, hi, Alonso. This is John Barras. Very interesting results. I have this question and then another one. We'll see how much time you have. But the first one is, what happens if I try to analyze the Carlini-Wagner attack, but with different dissimilarity measures? In particular, I'm interested in using Kurbla-Kleibler divergence or Bregman divergence and so on and so forth, which are better discriminators for distributions than L2 and L infinity, for instance.
So yeah, that was a question that we got during the camera, and yes, so we agree that using L2 norm might not be the best measure, because it has been shown that it works pretty well in images and it makes a lot of sense. But we don't have any knowledge of if other research has been done to analyze adversarial examples or the divergence in this type of problem setup. So it gives an open questions to find better norms that will be described.
One practical problem we're looking for, which is related to what you described, is the following. I have a router. I'm a distributor. I give you a router, and then you connect various kinds of IoT devices to your router. And I have no idea what you connected. And I want to be able, based on packet analysis, to find out what type of device you have. Because if I find that out, then I can actually put some defenses on the router that you put in. And any attempt to try to link on that, because there are databases here, especially at NIST, where people collect IoT devices characterized by their vulnerabilities. So if one could characterize them from the packet distribution, then you could actually use these databases to provide some defense against the routers that the network services provide, and then you hook up your IT devices. Anything that you are thinking of doing in that direction?
So currently we're dealing more with the adversarial part of the problem, but so from the results that we learn is that we get very good results on classification by just looking at the packet sizes. So I will imagine that it will be possible. I'm not sure how large is this data set that you mentioned or this database, the different IoT devices. But I will imagine that it should be successful to find or really capable. So probably a path that I will take in that direction is to see so what is the more important vulnerabilities or things that we cannot miss, and then based on that generate this classifier that makes sure that we don't make those mistakes when.
Okay, yeah, you can index them with the importance of vulnerability. Yeah, good. Thank you.
Thank you. Okay.
Yes, thank you. Thank you again, Alonso. Let's go to the next speaker. This will be Taha. Please share your screen.
Hello, everyone. Good morning. So give me a second. So can you see
Yes,
my
we can
screen?
see your screen. You can see your screen. Your 20 minutes start.
All right. Thanks everyone for joining. So my name is Taha Aftasad. I'm a PhD student at the University of Houston. Today I'm gonna talk about decision making in moving target defense environments. So I'd like to first start with what moving target defense is. Previously, traditionally, software companies hire security researchers to find vulnerabilities in their software and then refer them to developers to patch the software and fix a vulnerability. The problem is that no security researcher can find all the vulnerabilities in a single software. So right now, the software companies are adopting a proactive defense called moving target defense, which they use it to dynamically change the configuration of assets in control, such as their IP addresses, their software developments, and etc. These changing MTD configurations should be done continuously over days, weeks, or months. So right now, some system admins try to manually select MTD configurations to be deployed at each server. The problem is that it's time consuming because the system admin should consider constraints on deployment locations. He cannot change physical connectivity of servers, so it's another constraint here. And the resources the system admin has are limited. Also, the system admin should have some experience on the security of these MTD configurations. So we need some way to automate these deployment of MTD configurations. So for that, we need first a model for moving target defense, which has been discussed in literature. And the other one, which is the main purpose of this talk here, is a decision-making algorithm. So right now, the problem that we are trying to solve is that even with a small number of MTD deployment, MTD configurations and in control assets, the combinations of MTD configurations can be huge. Reinforcement learning has shown many applications in decision making, so we're trying to use reinforcement learning here for making decisions on MTD deployments. So in this talk, I'm gonna present an MTD model. This MTD model presents a game, and then I propose a solution of finding a decision-making policy as finding Nash equilibria of this game. We propose a double oracle algorithm for finding the MSNE of this game. We use reinforcement learning as the best response oracle in the double oracle algorithm. And finally, we propose our framework for solving the MTD game. Finally, I show that our approach is computationally feasible, stable, and viable. So the game is between an adversary and a defender.
they compete over a set of M servers. The adversary can probe a server with some probability. The attacker or adversary compromises that server, or if he cannot, it increases the chances of future compromising of that server. On the other side, the defender can reimage a server. It takes down some server for fixed time steps. It resets the progress of the adversary on that server, and if the adversary has compromised the server, the defender gains back the control. Each player in this model is rewarded based on the portion of servers that are in control of that player or are down. So the state of each server here can be presented with the number of probes initiated on the server since the last reimage, who controls each server, and then whether the server is up or down. So the point here in this MPD model is that the state is not completely observable to agents or players here. The adversary can have some estimate on the number of probes on the server because when the server was not compromised and the defender reimages it, the adversary cannot see that reimaging happen. The other thing is that the adversary can learn whether a server is up or down by probing it. The most important thing is that the adversary knows who controls which servers, so he knows when a compromised server is reimaged, but doesn't know when a server that was not in control is reimaged. On the other hand, the defender only sees the probes with some probability. He doesn't know which servers are compromised, and that's it. So the other thing we need to discuss here is the rewards for this game. We said that each player gains reward by the portion of the servers that are down or in control. For example, the model itself presents a couple of family of reward functions. For simplicity, I'm just simplifying these equations with some baseline parameters and present it here. One of the important things about reward is that the defender's reimaging cost is implicit. The defender doesn't gain any reward when the servers are down. But the attacker, when it probes a server, it pays some cost for that attack. We assume in our game model, so we want to find some policy for these players here. So first, let's define what a policy is. A policy is a function that you give it the observation from the environment and gives you an action gives the agent an action to be taken at that step in the environment. A pure strategy is a deterministic policy function. If you have a policy function for the attacker and a policy function for the defender, you can estimate. You can express the utility payoff of these policies with this formulation here, where gamma is the discount factor. When discount factor is 0, the agent only cares about the immediate reward, while when the discount factor goes toward 1, the agent cares about all the future rewards equally. So another thing we need to discuss is that we need to have some way to present or represent stochastic policies. A mixed strategy is a probability distribution over pure strategies. So you can calculate the utility payoff of two mixed strategies with multiplying the probability of that strategy happening. In our game model, we assume that the adversary and defender are rationals. It means that they both commit to strategies which maximize their own utility. So if one thing I need to describe is a best response strategy. It's a strategy or policy function that maximizes that player taking it, while the opponent commits to a specific mixed or pure strategy. If we take a best response for these two sites here, we can show that the problem of finding policies, optimal action policies, is equivalent to finding mixed strategy Nash equilibria of the game. The problem here is that we don't have these strategy sets for this player in this game, and we cannot enumerate them because the number of these policies are huge. So we use a double oracle algorithm which solves or finds the MSNE of a game based on a subset of strategy sets for each player. The double oracle algorithm iteratively finds a best response using a best response oracle to the opponent's mixed strategy Nash equilibria, which was explored until now, and then adds these new best responses to the strategy sets. It's guaranteed that the DO double oracle algorithm converges to an MSNE of the game. The problem here is that the DO double oracle algorithm is generally used with zero-sum games where all the equilibria yield the same payoff for both players. In general sum games, in our case, the game is a general sum game. It might have multiple equilibria where the payoff, the MSNE payoff for both players can differ greatly. So we need to face an equilibrium selection problem because it depends on the initial strategy sets and the output of the best response oracle. In experiments, we show that that's not the case in our game. So what's the BR oracle is a best response oracle produces a best response for one player while the other player is committed to some policy. Reinforcement learning can be used as a best response oracle. Why? Because it finds a policy which maximizes the rewards for that player choosing it. Reinforcement learning works on the set of experiences while doing trial and error on the environment. Each experience holds for what state was the agent in, what action it took, which state that environment took the agent to which state, and what was the immediate reward. One of the algorithms in reinforcement learning is Q-learning. Q-learning uses a Q function, uses a tabular approach for storing some Q values. Q values estimate the future rewards for that action in that observation state. You can optimize a Q table. You have a table with each entry is the Q value for each state in an action. For each action in a state, and then you can optimize this with with some samples of your experiences based on the Bellman optimization function. So let's integrate double oracle with our game model here. Here we have some problems we need to solve before completing the algorithm. First problem is that the state for both players is partially observable. They cannot see the state itself. For example, for the defender has some observes probes with some probability. So for example, let's take that the defender only sees 3 probes on a server. Does this mean that the server is safe, or does this mean that the server is compromised? We don't know. The adversary, on the other hand, doesn't know when the state of the servers has been reset when he has not compromised them. So to solve this issue, we add some extra features to the observation of defender and the adversary. For defender, we add the time since last reimaging and time since last probe, and for the adversary, we add time since last probe. The other problem here is that we need to, in each step of the double oracle algorithm, we need to find the MSNE of current strategy sets. The point here is that the MSNE of a general sum game, the problem of finding MSNE of a general sum game is p-path complete. So for a game of non-trivial size, we cannot find find the exact MSNE. Our solution is using a global Newton method for solving and finding the MSNE and finding the epsilon equilibrium instead of the actual MSNE. The other problem here is that let's take the defender. We have this many number of entries required for keeping the Q values in a table for the defender. It will not fit in memory, and we don't have enough time in our lifetime for exploring all the state action possibilities. Our solution is using Dpq Learning. We replaced the table for Q values with a neural network which only approximate the Q values for each action and a state. So we need to only compute hundreds or thousands of parameters. So for each, we have a neural network for each player. For the defender, for example, for each server, we have some features. We put one input neuron for each feature and one output neuron for each action to the action for that player. For example, for the defender, if we have 3 servers, each server have 4 properties. We have 12 input neurons. Because we have 3 servers, we have 3 output neurons. We can add an extra one for doing nothing for that player. So we can optimize these based on optimize our neural network based on the set of experiences we had. So our framework is like this. So we initialize the strategy set of each player, either with no op agents, no operation, the agents which do nothing, or we extracted some heuristics from the MTD model and then initialize the strategy set with these heuristics. While the MSNE payoff of the players has not converged, we iteratively find the MSNE of the game, train an adversary against MSNE of defender, and then train a defender against MSNE of the adversary, and assess these policies against each other and against our previous policies, and add them to the strategy sets. All right, so to show that our approach is viable, it's correct, we show that our Dpq learning indeed converges to the correct values. Well, it does. And then we show that our DO algorithm converges because, as I have mentioned, the DO algorithm converges to an MSNE of a game, but with true best responses. As we are using approximate best responses, these convergence guarantees are lost. But in our experiments, we show that regardless of initial strategy sets or configuration, the double oracle algorithm converges. It takes only 6 hours of training, which shows that our solution is computationally efficient. Another thing is that we need to show that our solution is viable, is correct. So we extracted these heuristics from the model itself, calculated the payoffs. Previously, the MSNE was here, and now we show that the DQL produces a better MSNE. We set up 10 servers with a training time of 1,000 steps. I mean, each epoch is 1,000 steps, and the discount factor is 0.99. Finally, we need to show that the solution is stable because because the approximators such as neural networks are initialized randomly. They can result in different equilibria for each player. So, but here we show that all these equilibria found are almost around the same value. So our solution is stable. Further, our policies are resilient to overestimation of the opponent. For example, if we change the cost of attack for the attacker, we show that the defender again gains the same amount of reward. All right, thanks everyone. Thanks for your attention. I can take any questions, or if you prefer offline, you can email me anytime. All right, thank you.
Yes, thank you, Taha. Thank you for the great presentation. So one general question about the double oracle. Can that work for more than 2 players, or is that restricted to 2 players?
Double oracle algorithm only works for 2-player games. Yeah.
I see. Thank you. Thank you. So there's no other question. So thank you for your talk. And now will be the time to go to the last talk of this session by Ryan Gabis. Ryan, are you online? If you are online, share your slides.
I'm online right now.
Good.
See if I can share my screen. You guys see this okay?
Yes, we can see.
Perfect, okay. All right, I have a recording because I thought that we had to upload videos. Turns out we don't, so I'll just play the recording, but I'll be around at the end if anyone has any questions. So, all right.
Perfect.
My name is Ryan Gabris, and the title of this talk I'm presenting is Lie Another Day, Concerning Bias in a Multi-Round Cyber Deception Game of Questionable Veracity. This is a joint work with Mark Polinsky, Joe DeVita, Kim Ferguson, Sonny Fugit, Justin Moget, and Brian Souza. We're all based on the Naval Information Warfare Center down in San Diego. So I want to start out with some motivation for this problem. This problem is motivated by the setup of fingerprinting and cybersecurity. So what's happening here is that there's usually, and what the attacker is trying to do is he or she is trying to find out more information about the environment which they're deployed in order to launch a more sophisticated attack. So the kinds of things the attacker might be interested in are what network services are being hosted in the environment, maybe which operating systems are running on the various machines, as well as what software applications are being run in the environment as well. So in order, the way that these techniques typically is that an attacker will usually send custom packets to the machines in the environment, and what those machines will then do is they will respond. And given these and the information contained in the response to these custom packets are going to include information from which an attacker can use to ascertain potentially what types of operating systems are out there, as well as what types of service configuration information which may be out there as well. And this is the information which can then be exploited by an attacker. So the fundamental question we want to ask here is, given this setup, what if the defender employs deception? And this naturally leads to the following types of questions. Given that there is an attacker within the environment, clearly the defender may not always want to tell the truth. And so when should the defender lie, given this setup? Another question which we'll be interested in as well is how long should the attacker engage a system? So at what point does it make sense for the attacker perhaps to either determine that it's not getting enough information about the environment, or determine that I have enough information about the environment in which I can now proceed to launch an attack. So our goal in this work was to distill a game of this form into the simplest possible incarnation we could. And one of the things that we wanted to do in addition to that was to have the defender then introduce deception into this environment. So for our setup, there's going to be 2 players. There's a defender, and the defender is going to control 2 machines, a real machine as well as a fake machine, which we'll also refer to as a decoy. The identity of these machines is known to the defender, but not to the attacker. The attacker then, at the end of the game, what's going to end up happening is, given the responses of various questions the attacker is going to ask, the attacker wants to determine the identity and then attack the real machine. So the way the game works is the game is going to proceed in rounds, where at each round, the attacker is going to probe one of the 2 machines asking about the identity of the machine, and the machine, which is then controlled by the defender, is either going to lie or it's going to tell the truth. Now, in order for the game not to sort of degenerate into a trivial form, we're going to assume that if the machine lies, then the defender is going to pay a cost. The defender can't just lie at every round or lie at exactly 1/2 of the rounds, in which case the attacker would get no information. And what's going to end up happening is, as I mentioned before, the game is going to end when the attacker decides to attack. So for our setup, I have the following illustration, which is sort of illustrates the core sort of mechanics behind our game. What's happening here is I have two machines that are at the top, a real machine and a fake machine, both of which are controlled by the defender. At the bottom of the screen, I have that little red circle with the horns on it. That's supposed to be the attacker. So the way our game works is that the attacker is going to first pick one of the two machines. In this case, it's picking the real machine, and it's going to ask that machine, are you a real or are you a fake machine? So the real machine then, or the machine it probes, is then going to create a response. In this case, that machine is going to respond that it is a real machine. Now, what I'm illustrating here with this bubble on the right-hand side is that's showing what the game looks like from the point of view of the attacker. So all the attacker knows that there's two machines that it can interact with, and it's probed the machine on the left once, who's responded that it's a real machine. So that's the end of the first round. Now in the second round, the attacker will do the same thing. It'll pick one of the two machines. In this case, it picks the fake machine, which is the machine on the left, and it asks that machine, are you real or are you a fake machine? Now in this case, the machine is going to respond that it's a real machine, and so you can see on the right-hand side, the attacker's viewpoint of sort of the game has been updated accordingly. In the third round, it's the same thing. In this case, the attacker is going to pick the real machine, and the real machine is going to respond that it is real again. So the attacker is going to pay a cost for probing, and the defender, we're also having the defender pay a cost for lying. The way that these terms work is that the defender is going to pay a cost of CF each time the fake machine lies, and then CR each time the real machine lies. Analogously, the attacker is also going to pay a cost CP for each probe. So we don't want the attacker just to have the ability to probe, as long as it wants to. And at some point, the idea is that the longer the attacker is engaging in the game, the more likely the defender could potentially figure out that something not normal is going on, and it can then potentially identify the attacker. So what will happen then is at the end of the game, based upon the feedback from these two machines, the attacker is going to choose to attack one of the two machines. Now, if the attacker chooses the real machine to attack, then what will happen is the defender is going to pay a cost of V. If the attacker chooses the fake machine, the defender pays a cost of minus V. Although the attacker doesn't know the identities of the machines, the attacker is aware of the costs that are associated with lying. So you can actually interpret this sort of as a worst case scenario for the defender, because the attacker has some information about the model or the environment which is deployed in. In particular, it knows the costs. So what will happen is that given that the attacker has this knowledge of its costs, the attacker is going to assume that the defender will act in a manner in which it will minimize its costs. And as I mentioned before, the game is going to end when the attacker decides to attack. So what will happen is the attacker will formulate a hypothesis test, which is based on the responses it got back from the two machines it was probing, to decide which machine is real and which machine is fake. And I'll show an example of that on the next slide. So what I'm showing here is this is an illustration of the setup that I had from a couple slides ago, where we have the attacker, and it's currently probing the real machine and the fake machine. And the responses it's gotten back are represented by that bubble on the right, where it knows the machine on the left has responded that it's real twice, and the machine on the right has responded that it's real once. So there's going to be two hypotheses. Point of attacker, either the attacker is either the machine on the left is real and the machine on the right is fake, or the machine on the left is fake and the machine on the right is real. So now what the attacker is going to do is, because it knows what the costs are for lying on the real and fake machine, it's going to compute the cost under both of these hypotheses. So under hypothesis 1, which is actually the correct hypothesis, the cost to the defender would be exactly CF, because the fake machine lied once. However, if hypothesis 2 are correct, then because the fake machine lied twice, the cost would be 2 CF. And if the attacker is going to assume that the defender is going to act in a rational manner in which it wants to minimize its costs, the attacker is going to assume that hypothesis 1 is correct, because that would infer that the defender is acting in a manner in which it's minimizing its costs. And so the attacker would then guess that the real machine is the machine on the left, which turns out to be the correct hypothesis in this case. So the contributions to this work are going to be the following. This paper is a continuation of a paper which we submitted last year at GAMESEC. And the paper from last year focused on optimal strategies for the defender in this scenario. For this work, what we're going to focus on is determining the optimal strategy for the attacker. And in addition to that, we're also going to simulate the behavior of the attacker as a reinforcement learning agent. So what I want to do now is I want to move on to the main analytic result of this work. So to ease the analysis, we're going to assume that the attacker probes both machines an equal number of times. And we're going to denote, again, the probability that the real machine tells the truth is going to be denoted as tau r. And the probability that the fake machine tells the truth, we're going to denote as tau f. Then what you can show is if we're given the setup where the real machine and the fake machine respond to the attacker's probes using a Bernoulli random variable with the parameter tau r and tau f, what you can show is the probability the hypothesis test is correct after n rounds is given by the following expression. So this is relatively straightforward to compute. And what we can do here is we can actually figure out what would the expected reward be after a certain number of rounds, which can inform us as to how the attacker should behave. So what I'm showing down here on these three plots at the bottom is I'm showing the normalized expected reward for various values of v. So what the normalized reward is, it's just that value v divided by CP, which is the cost of probing for the attacker. So if you look, for example, on the plot down here in the lower left-hand corner, what this is showing is each one of these plots represents the normalized expected reward for the attacker, given that the defender is behaving according to different values of tau r and tau f. As a concrete example of tau r, tau f is equal to 0.8, so the defender is telling the truth on both machines with probability 0.8. You can see that if the attacker wants to maximize their expected reward, they want to stop the game or they want to choose to run the hypothesis test after around 5 rounds. And what we see here is we see a similar trend for each one of these values of v. In particular, what we see is if the attacker wants to maximize their expected reward, what the attacker wants to do is basically play the game for a small number of rounds and then choose to attack. So that the thing to notice here that's being displayed across these three plots is that small number of rounds seems to increase with v. In particular, for the case where v is equal to 10, the attacker should only play the game for around 5 rounds. When v gets up to 100, then the attacker is going to want to play the game for a little bit longer, up to 10. And for the case where v is equal to 20, it's going to be somewhere in between those two. There is some variation with the values of tau r, tau f, but really the dominant trend here is the attacker should play the game. The number of rounds that the attacker should play the game is heavily correlated with the value v of the game. So what I'm showing here is this is the same information just displayed in a slightly different manner. So what this is showing is that if you fix tau r and tau f and then you give me the value of the game, what it's displaying here is it's displaying the optimal number of rounds that the attacker should play. So we see the same trends here as well. If the value of the game is around 10 to the third, then what that means is the attacker should play the game for less than 20 rounds if they want to maximize their expected reward. If the value of the game jumps up to, let's say, 10 to the fifth, then we do see that the number of rounds increases, but it only doubles, despite the fact that the value goes up by 2 orders of magnitude. So you want to play the game for more rounds, but it's a much smaller number of rounds than obviously how much v is going up for. So the question that we want to ask here is that given these trends, how long should the attacker play the game for? And what I'm going to do next is I'm going to denote that convolution. So this gamma is, I'm just going to denote the probability that the hypothesis test is correct by this parameter gamma. And the thing to notice here is that you can interpret gamma simply, what it is it's just the probability y2 is greater than or equal to y1, where y1 and y2 are binomial random variables with the following parameters. So what you can do then, because of the fact that there is this simple relationship between y1 and y2, you can actually express this quantity gamma as the sum of n over 2 IID random variables. So it's going to be each random variable can be denoted by xi, where xi is going to be equal to 1 with probability 1 minus tau r times 1 minus tau f. So this is the event that both the real and the fake machine lie. It's going to be equal to 0 with probability tau r times 1 minus tau f plus 1 minus tau r times tau f. So what this is this is the probability that one machine lies and the other machine tells the truth. Otherwise, that random variable is going to be equal to -1 in the event that both machines tell the truth. So what you can do if you apply this transformation is you can show that the expected reward of the game is at most this quantity I have at the top and at least the expression that I have down here at the bottom. Where again, what V is this is the reward for the attacker which is provided when the attacker attacks the real machine. So using these bounds, you can derive our main analytic result, which is being shown down here in the theorem box at the top. So let's assume that zeta is a constant with respect to V, and we're given tau R and tau F, which are both between 1/2 and 1. And the expected reward of the game is maximized when the number of rounds played by the attacker is at most proportional to the square root of V, or is at most sublinear with V. And this is consistent with the plots that I had, which are shown down here at the bottom from a couple slides ago. So the next for this work, as I mentioned before, in the second half of this work, we wanted to consider the performance of an attacker which is simulated using a reinforcement learning agent under a similar setup. Our main goal here is similar to before. What we want to do is consider how the value of V influences the length of the game as well as the decisions which are made by the attacker. We're also going to consider a more generalized version of the game, which I'll explain in a couple slides, where the attacker is also given to walk away without attacking. So the way our simulations work is the following. Similar before, the game's going to proceed in rounds. The game's going to begin at round I is equal to 0 with the game initially in the null state. Then in each round, the attacker is going to proceed by choosing one of the following actions. Either the attacker is going to choose to attack according to the hypothesis, or the attacker can walk away. So if either of these first two options is chosen, then the game's going to end. Otherwise, and similar to before, the attacker can choose to either probe the first or the second machine. So this, as I mentioned before, will continue up until the attacker chooses to end the game by either choosing to attack or walk away. In terms of the other thing that's going on here is the attacker is also maintaining a state vector, which is a history of the responses that it gets back from the defender. So these responses are the possible responses it gets back are shown down here in brackets where at each round, if the state is equal to R1, what that represents is that's the scenario where the first machine told the attack is real. F1 is the scenario where the fake machine, or excuse me, where the first machine tells the attacker that it's fake. And similarly, R2 is where the second machine says it's real, and F2 is the situation where the second machine says it's fake. So the way the reward function works is that at each round, the attacker is going to pay a cost, CP, for probing, and similar to before. Then at the end of the game, if the attacker chooses to walk away, then the attacker will not pay any additional cost or receive any additional reward for playing the game. If the attacker chooses to attack the real machine, then the attacker will get an additional plus V reward at the end of the game. Otherwise, if the attacker chooses to attack the fake machine, then the attacker will get a minus V reward at the end of the game. So the simulation parameters we used for our setup were the following. We allowed the game to proceed for a maximum number of 10 rounds. CR and CF were 2 and 1 respectively. The cost of probing per round for the attacker was equal to 1. The attacker was again simulated as a reinforcement learning agent in OpenAI Gym. It was run for 100,000 episodes. In terms of the parameters we used, we had a discount factor gamma of 1. The learning rate was 0.1. Epsilon parameter was 1. And the epsilon decay rate was 0.999. The one thing here that's a little bit unconventional is the fact that we had a fixed learning rate. And this was done because a fixed learning rate, for us, we chose to go with a fixed learning rate because we were trying to represent the setup where an adversary is slower to accept information in an environment where they might suspect a deception is occurring. And this parameter selection was actually motivated by that we did, where we tested human subjects, and it was shown that the suspicion of deception may or may not make it more effective. And in particular, it typically makes human subjects less willing to accept information that they're receiving about the environment. So what I'm showing here is this is the scenario where the defender is providing deterministic responses. The defender is either always telling the truth or it's always lying. And this was actually shown in our previous paper that under certain circumstances, these are the optimal responses that are given by the defender if they choose to maximize their expected reward. So for the scenario where the defender is always telling the truth, not surprisingly, the attacker learns to play the game for only a small number of rounds, after which it attacks, and it's going to get a reward which converges above 8. For the setup where the defender is always lying, what's happening here is that it depends. So we have 2 variants of this game. The middle row is the case where walk away is enabled, so the attacker is able to walk away after a certain number of rounds. The bottom one is the setup where we disabled walk away, so the attacker had to play the game. And so what was going on in this circumstance is that the attacker, for the case where walk away is enabled, it's always going to learn to walk away because the hypothesis test is going to fail. Otherwise, what will happen is the attacker will try to play the game and try to delay attacking for as long as possible, but eventually it has to attack, and it's going to get a negative reward at the end of the game. For the setup where we allow the defender to provide random responses to the attacker's probes, we can see that for the setup where the real and the fake machine responded truthfully about 90% of the time, we see similar behavior to the case where the defender was always truthful. In particular, the defender is going to play the game for a small number of rounds. Excuse me, the attacker will play the game for a small number of rounds, in this case between 2 and 3, and the reward is going to converge to slightly below 8. For the setup where the defender is telling the truth with probability 0.7 on both machines, something a little more interesting is actually going on here. So if we look at this middle plot, which I have highlighted, what's happening here is that the attacker is learning to play the game for roughly 3 rounds or so, after which it's getting an expected reward, which is approaching 4. However, what's interesting is that after a certain amount of time, we can see there's almost this asymptotic shift in the behavior of the attacker, where the attacker is learning to actually walk away. And this is contrasting with the scenario where when we disabled walk away, we see that the attacker can actually achieve an expected reward of 4. So what we're going to refer to this suboptimal behavior as, because clearly, the shift in behavior is not maximizing the attacker's expected reward. For whatever reason, the attacker's learning that walk away is better than playing the game, which is clearly not. We're going to refer to this as a trap. So what this trap is caused by the scenario where the attack action is chosen and the cost hypothesis is actually not going to be correct. And this event always has a small but non-zero probability, and so it's going to eventually occur if the game's played for long enough. In our scenario, because of the fact that we have this alpha parameter set to be a fixed value, this event has the overall effect of setting the expected reward for attacking within our Q tables to actually be negative. And so what will end up happening is that walk away is always better than that negative reward. And so eventually what's going to happen under our setup is that the attacker will always learn to eventually walk away. And again, this is really a function of the fact that we set the alpha decay to be so small, and that again was motivated by the scenario where we wanted to simulate the behavior of an RL agent who may not have a lot of confidence in the environment in which they're operating. What you can do to avoid the trap is actually pretty simple. You can simply just force the exploration parameter epsilon to never drop below a given threshold. So for our setup that I had on the previous slides, for the case where v is equal to 10, you can see that by setting the threshold to only 0.2, you're able to recover a large portion of that expected reward as the game is played. So fundamentally, what the trap is caused by, it's the result of a single outcome which causes the agent to always walk away. And this behavior appears to be similar to what we see with the law of numbers. And what the law of small numbers is, it's a human cognitive bias to believe that the outcome of a small sample will be representative of the larger population. So one of the questions that we had is, maybe is it possible to arrange the game's parameters to trigger risk-seeking behaviors to make maybe the attacker keep playing the game versus walking away prematurely. In terms of conclusions and future work, the contributions to this work were the following. We generalized our previous model, which was introduced in the paper we had last year. We also determined the optimal strategy for the attack under this model. We showed in particular the number of rounds the attacker should play the game for is going to be sublinear with respect to V. We analyzed the behavior of an RL agent playing the role of an attacker, and we were also attempted to relate our analytical and empirical findings to cognitive bias. In terms of future work, we're looking at potentially increasing the number of machines to see how that affects the game as it's played out, as well as allowing the defender to influence the attacker's belief of which machine is real and which machine is fake. In addition, we'd like to potentially do things like see if we can augment our framework by incorporating things such as bias effects or the sunk cost fallacy. So thank you very much for your attention. I'd be more than happy to answer any questions.
Are you guys still with me? Hopefully.
Hi, yes, I am with you. I think Charles has some problems with his microphone. This is John Barras. Hi. Thanks for a nice talk. I have a question. I don't see another one. Okay, so the question is that in real situations, right, these things will operate asynchronously, meaning the defender and the attacker will operate asynchronously. And it's the same when we have groups of attackers and groups of defenders collaborating. So the question is, does the order of observations and actions matter here? If I observe first and then act, or I observe and then act, and so on and so forth, is that?
So I mean, yeah, under our model, it absolutely matters because what's basically ending up happening here is that we're, excuse me, let me rephrase it. For our model, it actually does not matter because of the fact that we're assuming that the game's going to go on for a certain round.
Right,
So
yeah.
what matters is after a certain time, what's the total count?
Right.
We actually implemented this differently in our previous paper. There, it actually did matter. We simplified this really because we wanted it to scale. So we were able to run more simulations for longer periods of time. And but it is an interesting question to look at it where you do take into account the order of the responses you're getting back. Our biggest problem was just in terms of scalability. We were having a hard time running it for more than just
the deep reason why I'm asking you is because we know from other work we are doing and the work of others that order matters when humans are involved.
Yeah, absolutely does. Yeah.
Because there's some other theories that people have developed and validated where, if the attacker acts first, the defender, and so on and so forth, the order is it's a complicated phenomenon. We don't understand it, but we know that under certain circumstances, order is important. That's why I asked you the question. Okay. Anybody else has any other questions? If you have, let's put it on chat or.
Yes, I can listen. So thank you.
Okay.
Thank you, all speakers, and thank you for attending this session. So we are now going to follow by, I believe, a 15-minute break and come back for the keynote.
Yes, thank you all very much for attending. I want to make a small announcement that I forgot to mention in the morning. I will ask a small group of people to actually give us input, very small group of people like we do every year, because we are going to select the best paper award and we'll announce it Friday. We will finish the selection by Thursday, and the people that they receive the award, they also receive a $500 honorarium for the prize. So I forgot to mention that in the morning. My apologies, but it will happen. Thank you very much.
Oh, thank you all.
John, we cannot hear you.
We should put the break slide I sent you. Somebody put it up. Maybe Yarada, you can do it since you are the next chair, right?
Okay.
Do you have the slide that I said that we are in a break and something? Can you take control of your screen and put it up? You have it, or you want me to do it? Radha. You have the slide, or you want to put it up? I can't hear you. Okay, I'll put it up. Oh, you have it. Right, very good. Very good, thank you. Okay, I'm going to disappear for a few minutes.
Good morning or good afternoon.
Hello there. We're on break until 1 o'clock Eastern Standard Time. So you got about 8 minutes.
That's good news.
Yep. Thank you very much.
Jens, can you hear me?
Yes.
Okay,
good afternoon.
Great. Good afternoon. So you are all set with the slides and everything?
I think so.
That's great. This is very nice. Thank you. Yeah.
Oh, many thanks for the invitation. I am grateful for the chance.
Let me see if that's great. Those are the cherry blossoms of the University of Washington.
That is lovely. So I'm thinking, I think it was last year I went to Taiwan and we had to go all the way up to the top of Alishan, which is one of the tallest mountains in Taiwan, to see the cherry blossoms. They have them up there on the mountaintop, but you have them right on campus of University of Washington.
In the quad, yes.
Amazing.
And also the main administrative building walking towards the fountain, which then opens up all the way to the Rainier Vista, which has a view for the Mount Rainier.
Sounds good to me.
When it shows up. So I take it that you haven't visited University of Washington yet.
I have
Okay.
a bunch of times, but I think I don't come at the. I managed to get at all the wrong times when the cherry blossoms are not there. I need to work on that.
Yeah. Around springtime is the best.
Ah, yeah. So that's the trick. I will take a mental note of that.
Yeah, we have Quantum X program in the seminar. You probably know the group that is doing some stuff here too with the physics and yeah.
They had a sort of a national meeting a month ago. I was a speaker there too.
Yeah, Kaime is joint faculty with physics, Kaime Fu.
Oh yeah. That's very good. And I think it's a bit like you have the advantage of being close to Microsoft and we have the advantage of being close to Google. We are like all of 5 miles away from Google's main quantum operation, which is very convenient. And to make it more convenient, the guy who is the program manager for the quantum group is married to the woman in the next office to me. So we see him quite often.
I see, yeah. We do have fairly close ties with the Microsoft research side of the.
Yeah, it's an excellent group. And of course, not just those located in Redmond, but quantum people at Microsoft spread all over, particularly in Europe.
Yeah, I got to know them when we were doing a little bit of recruiting in this space earlier, and we are actually looking to hire 2 people this year.
Very good.
Both through the department. 2 of them.
Hi, Jens. Welcome.
Hey, good afternoon. And thanks for scheduling me at a time that's really convenient to me.
Yeah, thank you. It worked out very well for the East and the West Coast. And hopefully others too, because there are quite a few people from Europe and China and Asia.
Australia.
Australia,
Hi.
yeah.
Hi, Jens. Welcome.
Hey.
How are you doing?
Doing well. Doing well.
Okay.
I'm enjoying that I don't have to sit in Los Angeles traffic every day at the moment.
I cannot share with your enthusiasm. I feel like I'm in prison, but that's okay.
Yeah.
I was just reading an article this morning about how this closed in has changed the behavioral aspects of people with respect to work.
Yeah.
And not all of it was positive, actually. So.
That is, I agree. I agree. I think there's a whole bunch of graduate students out there who now have nothing else to do than to do research. So in a way, I think that the research productivity of the computer science community has probably gone up.
Oh, come on. I don't think so. I mean, it takes a tremendously strong individual to have this self-discipline to sit down and do research all the time. I mean, I think the office interaction is essential.
Yeah, it is. So maybe there's going to be a crash in that all the projects that were already started and going and people could do without too much supervision, they will do great. And then after that, productivity will stop.
I don't know about that, but it's just, you know, as always, I mean, I'm from Greece, always will say, you got to have balance, okay? You need to be somewhere balanced in the two approaches, yes.
Oh man, so my second to last plane trip before today was to Athens last year in November. And then I haven't been doing much since then because of all this shutdown.
Yeah. I haven't traveled, I rather know I travel a lot, I haven't gone anywhere. Not even to another state since March, you know, I mean, that's crazy. Oh, no, I'm sorry. I went twice to New York to see my son, that's about it. But now even in New York, you have all these crazy rules, like the governor and others have put over there. So you have to be careful.
Cannot do much. Yeah.
Okay, you are on, eh? So
yeah.
I give it up to you, Radha, when you want to start with you. You're handling everything now, okay?
Yeah, I'll pretty much start. Just want to make sure we want to make sure that Jens can share the slides once I finish the introduction.
Yeah.
If you want to try to bring it up,
I can try.
fine.
Let me give it a, can you see?
Oh, perfect.
Something?
Yeah, we can see that. Yeah.
All right.
Great. Good afternoon and welcome everyone back to the GAMESEC first day. It's my great pleasure to introduce our keynote speaker today. Dr. Jens Palsberg is a professor and former department chair of computer science at the University of California, Los Angeles. His research interest is in the area of programming languages and compilers, and he teaches quantum programming as well as classical compilers. He's a member of the NSF Quantum Leap Institute that was established in 2020 and is led by Berkeley. This institute tackles far-reaching questions at the heart of quantum computing. He is also a member of the ACM Executive Committee, the chair of the ACM SIG plan, and a member of the editorial board of Information and Computation. In 2012, he received the ACM SIG plan Distinguished Service Award. With this, I invite Dr. Jens to give you a keynote.
Thank you. Quantum computing has been relevant to security ever since the discovery of Shor's algorithm for factoring integers. And now quantum computers are here, and researchers are building the quantum internet. And now we need quantum security. And as much fun as it is to break security, what we really need are techniques for improving quantum security. And today I want to persuade you of the potential in a new research direction on quantum security games. And really what I'm doing here is that I'm picking up on that your community are the experts on security games. And I want to put quantum in front of that. And I'm going to go through 3 points in support of this direction. I'm going to give a review of quantum computing and touch on the math of quantum computing. Then I will talk about quantum games and touch on how to formalize them. And then I will discuss 3 directions for developing quantum security games that I think are interesting or look potentially good to me. And so let's start with what is quantum anyway. And this is a qubit. Really, a qubit is a little vector of 2 complex numbers. So alpha and beta here are complex numbers. And as it happens, the largest quantum computer today has 72 qubits. It's at Google. And the thing is that if you have 72 qubits, you're really computing with 2 to the 72 complex numbers. That's how it works in quantum computing. Every time you get another qubit, you double the number of complex numbers that you're working with. And so it means that if we get to 300 qubits, which the National Academy says we will within a few years, they expect, we would be computing with 2 to the 300 complex numbers. And 2 to the 300 is already more, it's a number that's bigger than the number of atoms in the known universe. So just gigantic numbers. And so that power is really what makes quantum computing powerful. And the thing is, quantum computers are getting better at a double exponential rate. One exponential is from a linear growth in the number of qubits. We already talked about that exponential. And the second thing is a linear improvement in the quality of every component on the quantum computer. And given the many components, when each one improves linearly, you also get an exponential improvement there. So a double exponential improvement in how good quantum computing is. So we want to harness this power. But before I get to that, I want to talk about where do these complex numbers come from? And so now we are going to the heart of quantum mechanics. And Feynman said that the essence of quantum mechanics is the double slit experiment, which many high school students in California actually do as part of their high school science education. And so I just want to touch on it a little bit. It's an experiment that goes back to Thomas Young in 1801. And they did the following. So to the left here, you see a light source that's beaming photons at a wall with 2 gaps or 2 slits, as they like to call them. So the photons can go through either one. And then there's a back wall. And on the back wall, we put up a little marker of an area P, where we say we are particularly interested to know whether the photons hit P. And then the double slit experiment is to do 3 variations. First, you beam the photons so that both slits are open, and some of them will hit P. Then you cover up one of the slits, and you see how many go through the other slit. And then you cover up the second slit, and you see how many go through the first slit. And now you should expect that in some sense, the first one is equal to the sum of the next 2. But that's not true. So that's the thing where quantum mechanics start to really have different math. And so the problem here is that when we talk about what's the probability that a photon goes through when both slits are open, we think of that as a classical probability between 0 and 1. And then when we cover up one of the 2 slits, we're still thinking classical probabilities, and we expect that we get 2 probabilities that sum up to the total, but they don't. It just doesn't work that way. And so what people discovered is that the way to make it work is that you have to change the probabilities to complex numbers. And once you do that, everything totally works out. Now you can actually add up two probabilities expressed as complex numbers, and you get the third one, and everything is good. And so what the people in quantum mechanics do is that they change the name. They no longer call them probabilities, they call them amplitudes. But the point here is, for me, is that those probabilities, well, amplitudes as complex numbers, those are the complex numbers that we see in a qubit. And so we are really, when we are computing with qubits, we're really at the very bottom computing with the complex numbers that we get from quantum mechanics. And so this is where there's this famous slogan that God plays dice, but they are not normal dice. They're kind of complex dice in a way. At least they give complex outcomes. That's where that slogan comes from. All right. So we have these complex numbers, and I already start to talk about quantum mechanics. And so the next question is, how much quantum mechanics do we actually need to know to work on quantum computing? And the answer is we need to know nothing. And so we can sort of make a little chart here where we can think about, first of all, how quantum computing relates to classical computing, and second, what is a convenient interface to what's really going on at this hardware level. And so just like we can think of a classical computer as a, let's say, a Turing-complete machine for doing Boolean algebra, quantum computing is a machine for doing linear algebra. And so in a way, linear algebra is much more restricted. And so it means that whenever we have a problem that can fit under quantum computing, that means sort of under the linear algebra hat, then we're good. And otherwise, we would go to classical computing. So already this chart here sets up how we should think of a quantum computer. We can think of it much like we think of a GPU, that it's something that's not good for everything, but when it's good, it's very good. And so so a quantum computer is like an accelerator, and we should use it when it's really good. Underneath, of course, sort of the algebra level, there's a hardware level that's very complicated. And the good news is that for thinking about quantum computing, we don't have to know about it. And the reason is that there are 4 postulates, or we could call them axioms, that governs this interface between the quantum computing linear algebra level and then whatever quantum mechanics goes on underneath. And those postulates say in outline that number 1, the state is a vector of complex numbers. If we have 1 qubit, it's a vector of 2 complex numbers. And if we have n qubits, it's 2 to the n complex numbers, but it's a vector. The way we do computation is that we apply one matrix after the other to this vector, and eventually we get our result. And the third thing is that we can, at the end, we can read out some information, some partial information about the final vector. We cannot get to know exactly what the final vector is, but we can get to know something about it. And that getting to know is called measurement. And so it means that, and then there's sort of one more thing that is what people normally call superposition, which is that this vector can have non-zero numbers all over if it wants to. Of course, the simplest vectors will have a single 0 and a single 1 and all the rest of them zeros. But here we can have a vector with as many non-zero entries as we like, and that's normally called superposition, or as we would say in linear algebra, it's a linear combination of basis vectors. And so it means that when we are computing, what we're really doing is something like this. If we want to do quantum computing, that's the thing in the middle. And so first we start with some bits. So we have a classical computer that needs some work done. It takes some bits, loads them up to the quantum computer as qubits in a sort of very sort of basic state. And then after that, we'll do our quantum computing. We will get a vector of qubits out of that. And then at that point, we can measure, and that gives us back some bits, which the classical computer can then use for continued work. And so all this computing in the middle is doing linear algebra. And so there are restrictions. We cannot do all linear algebra. But for now, just think of it as all computation steps are to apply a matrix. And it turns out that very good application areas for this. Of course, we talked about Shor's algorithm for factoring integers really fast. There are other areas that people are excited about. There's particularly simulating quantum chemistry, which was one of the original motivations for starting quantum computing in the first place. And so in particular, better simulation of quantum chemistry may lead to, for example, faster drug discovery. And then I should mention solving NP-complete problems approximately, which is DARPA is running a program at the moment where they put $33 million into using quantum computers to solve NP-complete problems approximately. Another very promising area. So then we talked about superposition, but then there's another thing that makes quantum computing powerful, and that is entanglement. And so what is entanglement? And so we can sort of look at it here and say, if we have 2 qubits and we get to the point where we want to measure, what entanglement means is that those 2 qubits will collapse to the same bit. It's like when you measure them and you get out a bit. For those 2 qubits, you will always get the same bit. And so this is where I want to get a little bit closer to the math of quantum computing. And I want to talk about how to produce a famous entangled state, which is this one here. It can be written in different ways, depending on how we like it. The notation on the left is called Dirac notation, after Professor Dirac. And it is a way of expressing that we are working with 2 qubits. And what we are seeing here is that one possibility is that both qubits are 0. The other possibility is both qubits are 1. And then there's a constant in front of it to make all the math work out, which I'm going to skip the details of here. And it turns out if we want to write this as a normal column vector, it comes out this way. And what this is saying is really that this thing over here, which is the 0, 0, that becomes the 1 up here in top of the vector, and the 1, 1 over here, that becomes the 1 at the bottom of the vector, and then the constant factor in front of it is still there. And so there's just different ways of expressing vectors, and we can talk about why this is, but today I'm just going to be sort of very loose about it. And what I do want to talk about is, how do we create this entangled state? And then as I go on in the talk, I'm going to cook a lot of soup on this very famous state here. So here's a program for constructing this state. So we are working with 2 qubits. I'll call them qubit 0 and qubit 1. And as you saw, I need to load up something to get going. And so I'm loading up with typos and everything. I'm loading up the bit 0 and the bit 0. And so now that gets represented as this 0, 0 notation from the previous page. Now I'm going to do computation steps. And as I said, every computation step is to apply a matrix. And so I'm picking 2 matrices here. One is called H, which is short for Hadamard, after Professor Hadamard. And then C0 is another gate. As they like, this is quantum computing. They like to call the matrices gates because they think they make them closer to hardware. But for what it's worth, they are matrices. And the program here is really 2 steps. So first apply H to the 0th qubit, and then the C0 is operating on 2 qubits. And so it's operating on both this qubit number 0 and qubit number 1. And in quantum computing, they like to write this kind of stuff as diagrams. So to the left, we have the initial state. Each qubit is now sort of has sort of a line going with time going from left to right. And then first we are applying this Hadamard to the qubit number 0. And then there's the C0 gate that somehow does an operation on both of these. And these H and C0, they're really matrices. Here they are. So they are, in the case of Hadamard, working on a single qubit. It's a 2 by 2, so it can transform a single qubit, which is a vector of 2 complex numbers, into another vector of 2 complex numbers. And then C0 is working on 2 qubits, so that would be a vector of length 4, and it will transform a vector of length 4 into a vector of length 4. And if one works out the math, one will actually get to this state here. So just apply the matrices, and now we have it. And so, so again, this state is entangled because if we measure, we will either get this 0, we will get that both of the bits are 0, or we will get this, both of the bits are 1. And so that's exactly what entanglement means. Now I want to talk about what this has to do with the quantum internet. And so, so of course, I'm in America. The White House this year called for the development of the quantum internet, and there are multiple centers devoted to this effort. One of them is a $50 million NSF Engineering Research Center led by Saikat Guha at University of Arizona. Another one is a $25 million NSF Quantum Leap Challenge Institute led by Brian DeMarco at University of Illinois. And they're working hard. They have great ambitions to build the quantum internet. And the question I want to raise is, how will this possibly work? And there's a huge challenge right up front, which is in quantum computing. Once you dive further into the math, there's a property that is like an ironclad property, which is one cannot copy an unknown qubit. That's called the no cloning theorem. And so if you cannot copy an unknown qubit, how are you going to build a repeater for an internet? So, you know, internet is all about connecting computers that are far away from each other. And one of the ways we make that happen is we have repeaters. And so what does a repeater do? It takes in a packet of stuff and then it sends it on. But if we cannot sort of take this thing in and forward it, so we need to kind of store it for a moment and then forward it. If we cannot copy an unknown qubit, how is this going to happen? And it turns out that this is where this entangled state from before comes to the rescue. And this brings us to how the quantum internet is really going to work, which is it's going to work by quantum teleportation. So rather than sending qubits in whatever sort of just send the qubits and they will somehow keep forwarding until it gets to its destination, we're going to use one of the really classical techniques from quantum computing, which is quantum teleportation. And I want to explain how this works. And so we're going to have the two usual parties, Alice and Bob. And Alice has a qubit. And let's just say that it looks like this. So this is actually how we express a qubit in superposition. So really, this is the same alpha beta that I showed earlier, but now I'm writing it in Dirac notation instead, so that it's a linear combination of two basis vectors. So both this thing that's usually pronounced ket0 is a vector of two complex numbers, and this ket1 is a vector of two complex numbers. And now Alice wants to send this qubit to Bob. And so what they do is that the first thing they do is that they share this entangled state from before. And so that's already, you know, a challenge. So they need to share an entangled state. But let's say that they can do that. And now we move Alice and Bob fairly far away from each other. And now there are 3 qubits in the system. This funny operator in the middle here is tensor product, and I'm going to skip the details of what that has to do with anything. I'll simply say we have a qubit here and we have 2 qubits here, so there are 3 qubits in the system. And now let's just look a little bit at the protocol of doing quantum teleportation. And so really we just want to get this qubit over here over to Bob. That's what we want. So what's going to happen is the following. So Alice will keep 2 of the qubits. She will keep, of course, she has this qubit already. And then in the entangled pair, she will keep the first qubit. And then the second qubit, Bob has the second, I guess it's the third here. The second qubit of the entangled pair, the third qubit of the system, Bob will have that one. And so whatever's in the red box, Alice has that. And what she does is that she executes a little protocol. You can see she's using the same kind of matrices from before, but the program is just a little bit different. Now we are executing things in a little bit different order. She executes that on her 2 qubits. Then she measures them, which will give her 2 bits. And then she will send those 2 bits to Bob. And this is already here sort of an insight in how quantum teleportation works. It's actually working by sending 2 classical bits over the network. And it's relying on that there's already something being shared up front, which is this entangled state. So Bob gets 2 bits. And so what is he going to do? And so let me just show a picture of what Alice is really doing to give you a sense of what the math is like. So we have the state from before up here. By the laws of the tensor product, this can be rewritten like this. So it becomes very explicit that the system is in one out of is in superposition of 4 different basis states. So a linear combination of these 4, and then we can apply the C0 matrix, then everything gets transformed this way. And so we can talk about how this works, but that's just the rule of this matrix. And then when she applies H, she gets everything down to, after some calculation, down to this one here. So this is just sort of going through the rules of linear algebra. So now we have that. And then she measures. And as you can see, when she measures her 2 qubits, so either the first 2 qubits are 0, 0, they're 0, 1, they are 1, 0, or they are 1, 1. And then the third qubit is whatever it is in each case. And what this thing here is saying is that once you do the math of it, is that each of these 4 cases happen with probability a quarter. So they're all equally likely. So there's something about quantum computing where you have to take this constant squared to make it work. So, so you get a quarter. And then she sends those 2 qubits to Bob. And here's the big picture. So we have Alice up here with her 2 qubits. She does the little protocol. This is trying to say that she's going to measure. And then she sends her 2 qubits not qubits. She's sending the 2 bits that she got from measuring over to Bob. And so now Bob is looking at that. And he's going to execute his own little protocol using yet 2 other matrices, which I will skip detailing what they are, but I can explain them in English as I will do on the next slide. But he's going to do a little bit of his own quantum computing. And eventually, once he's done with that, he will get the qubit. So Alice had a qubit, and after this is done, now Bob has the qubit. So that is quantum teleportation by sending 2 classical qubits over in the middle. And so what Bob actually does, just to sort of touch on this, is that he says, I got this. So the state of the 3 qubits is now all of this. And of course, Bob cares about his qubit, which is the stuff in the blue boxes. And so you can see his qubit in different states. There's actually 4 different states suddenly this qubit is in, just because Alice was doing something. So that is the magic of entanglement, that because Alice has a qubit that is entangled with Bob's qubit, when Alice does something to her qubit, which is she does some computation, she does measurement, then stuff happens to Bob's qubit. And so what Bob will say is, if the second qubit he received is a 1, then he will apply this X matrix to his qubit. And if the first qubit that he, or the first bit that he received is a 1, then he will apply the Z matrix to his qubit. And it turns out that if you translate this to sort of something we can read easily, then if he receives 0, 0, he will do nothing. If he receives 0, 1, he will swap the 0 and the 1 here. If he receives 1, 0, he will flip the sign of beta. And if he receives 1, 1, he will do both of these operations. He will both swap 0 and 1, and he will flip the sign of beta. And boom, there you have it. No matter which case we're in, he will end up with his qubit exactly like Alice's qubit from before we started the teleportation. Of course, it goes without saying that Alice's qubit gets destroyed. So we still, no cloning is still in effect. We cannot copy an unknown qubit. And so the way that we sort of get over that is that we destroy Alice's qubit in the process. So this is what's going on. This is quantum teleportation, and this is what the quantum internet will rely on. And so let's just look at where we are with the quantum internet. So in 2016, researchers from Canada did an experiment in Calgary where they used the fiber cable network of Calgary to teleport a qubit for 6 kilometers. That's more than 3 miles. They were not doing teleportation. They were simply sending a photon over the fiber cable network. And then 2017, very famous experiment, this time researchers from China teleported a qubit up from Earth to a satellite in orbit. So that's a teleportation over 1,400 kilometers. So more than, it's up around 900 miles. But still not using repeaters. And so now we get to 2020, this year, and Lukin at Harvard showed for the first time how to build a quantum repeater using the kind of technique that I just went over here, using teleportation. And so it means that the big sort of, let's call it sort of technology problem of building the quantum internet is now at least solved by a lab experiment we have a repeater, and now it's sort of an engineering problem, if you like, to really scale this up and make it work at, say, the level of a whole country. And so so it means that we can look at the big picture as follows. We have a sender over here who's somebody doing quantum computing. They want to send a qubit to the receiver over here. And the way this will work over long distances is that you teleport the qubit, and the repeater in the middle is executing this this protocol that I just went over of quantum teleportation. And that leaves just one more challenge for the quantum internet, which is we want to do more than just sending a qubit over from Alice to Bob. We want to be able to entangle qubits on two different quantum computers very far in between them. And so I just want to make a remark that if you look up Wikipedia, for example, or other places, you will find a picture like this. And so what people are doing here is that they're trying to talk about both getting a qubit, as we can think about this, send over from here to there over, as you can see, two bits. That's the classical channel. That's sending the two bits as quantum teleportation. But they actually talk about more than just sending a single, I'm sorry, they're talking more about sharing a single entangled state. It turns out that if you really want to entangle qubits with Alice with qubits over with Bob, you need more. You need actually a pair of entangled states. So before it was not enough to have a single entangled state, but if you have two, now you can start to do even more and entangle Alice qubits with Bob's qubits. And so so that is the principle upon which people are building the quantum internet. So that was quantum computing. Now I want to talk about quantum games. And well, we know about how to formalize classical games. We know how to work out an equilibrium if we can get all the formalities right. And we certainly know how to use games, classical games, to solve problems in computer science, particularly in security. And so now I want to talk about what is then a quantum game. And as an example, I'm going to use quantum chess. Quantum chess was developed by Chris Cantwell out here in Los Angeles. He's at USC. As his PhD project, he developed quantum chess. Of course, there are many ways you can take a classical game like chess and make it quantum. And so he did one of those, and the one that he developed I particularly like. And as it happens, I have a Steam account on this computer here for the purpose of playing quantum chess. And so what I will do is to just show you a little bit about how these concepts of superposition and entanglement enters the game when we do quantum chess in this case. And so let's look at this board. What you see here is the white king, a white pawn, and a white knight. And up here on the other side, we have a black king and a black pawn. And of course, if this was classical, we know all about what the rules are. But now we are going to make it quantum, and we're going to do this in sort of Chris Cantwell style. And in fact, these things I'm showing you are screenshots from quantum chess, as you can find it on the internet. First idea is that a piece can be in superposition, which really means the whole board can be in superposition, so that the board that you are seeing is really a linear combination of different boards where each board has a different probability. And the way we can represent this idea is that we can say when we move, for example, this knight, we can move it either classically, we simply move it the way knights move, or we can move it quantumly, which means that in this case, that the knight can do two steps, but only with 50% probability. So for example, here we can decide to move the knight here and then over there. But now there's only 50% probability that it moved and 50% probability that it stayed where it was. So this means that this board here really represents a linear combination of two boards, one where the knight is here and one where the knight is there, and each one with 50% probability. So that's superposition. So we have that already right there. So we've done this quantum move. Now it's black's turn. Black gets the idea to move this black pawn and wants to move it 2 squares forward. And the question is is that even possible? Because what if the knight is there? The knight is actually the knight is blocking the pawn. So what does this mean? It means that now we get entanglement, because now it depends on whether the knight is there. And so what I did here is that I copied this thing over, and what I'm doing is that I'm saying, well, we are going to move the pawn maybe with 50% probability, that which is depending on the knight. We move the pawn, and with 50% chance, it just has to stay where it is because there was a knight there. So now we have entangled the knight and the pawn. And if we look at what's the probability of each possible board here, now we are down to something like 25% of 4 different boards, but represented in a very nice way here in this situation. So now we have entanglement. Now it's white's turn. And white gets the idea of moving the pawn 1 step forward. And of course, this now depends on whether the knight is there. If the knight is there, then it cannot move. But if the knight isn't there, then of course, now we know with certainty that it's over here. And then we can move the pawn up here. And this brings me to another point that Chris Kent will build into quantum chess, which is only 1 piece per square. Even if there's only some probability that the piece is there, there's at most 1 piece per square. And so it means that when we move this pawn forward, or rather try to move it forward, we are triggering a measurement where we need to know, is this knight really there? And so one possibility, so I'm again copying this thing over to the left, one possibility is that the knight was not there, then the pawn can move forward, and then we know with certainty that the knight was over there. And if it is, then it means that this pawn couldn't move. So now we know with certainty that the black pawn is there. So that's one possibility. The other possibility, of course, is that the knight never moved. And so now we have this situation. The knight never moved. This means that the white pawn didn't move. And this means that the black pawn was free to move forward. So we know with certainty that the black pawn moved forward. And so that is quantum chess. This is how you get superpositions, how you get entanglement. And you can find videos of international masters in chess trying their hand at quantum chess on YouTube. And so what we see here is a way to think about how to take games as we know them and make them quantum, or for that matter, just design quantum games. And so there's some things to note. So first of all, the board is described as a vector. In quantum computing, one of the things about these matrices that we apply all the time is that they are all invertible, which is another way of saying that quantum computing is reversible. And so it means that we have, when a piece takes another piece, we have to model that this is reversible. And so another way of saying that, which is what Chris Cantwell does in his implementation, is that the wooden box of pieces that have been taken and are no longer on the board, they are part of the game as well. And so when a piece moves to the box, there's actually a reversible step that puts it back on the board. And every step that's taken in the game is done using one of the matrices that are allowed in quantum computing. They're called unitary matrices, and in particular, they are invertible. And so what you can see is we can have a game with superposition, we can have a game with entanglement, and that is the kind of quantum games that I have in mind that we should be thinking about for quantum security games. Okay, so in this case here, of course, we have these two parties. One is playing against the other. It's totally possible to have team play as well, where where multiple players are on the same team. I just want to mention a famous game, which is not chess, but which is a different game called the Magic Square game. So this page here you can find on the internet. And what's going on here really is that now Alice and Bob are on the same team, much like they were when they were trying to get a qubit from Alice to Bob. And so the thing to note here is that there's a game, there's this 3x3 grid, and there's a referee who tells Alice to put in, so the referee will pick a row and tell Alice to put bits into that row, and they have to sum up to 1. And then totally without coordinating between Alice and Bob, the referee tells Bob to fill in a column. The referee picks the column and then says fill in bits into this column in a way that sum up to an even number. And then, so Alice and Bob are not allowed to coordinate in any classical way. And they win if they end up putting in the same bit in the overlapping square. And they lose if they put in two different bits. And so, so of course, Alice and Bob, they cannot coordinate classically. So what they will do is that they will act at random. And what one can show is that they will win with 89% chance. So that's just what it is. So they will not always win, of course, as the example shows, but they will win with a very high probability. However, if they can start to use quantum teleportation, or rather simply have an so we don't need to go all the way to quantum teleportation. All they need is this entangled qubit. So two entangled qubits that they share. Alice has one, Bob has one. They are entangled. Now one can start to coordinate in a quantum way, and that coordination is enough to win 100% of the time. So that's sort of a famous theorem in quantum games, is that this is possible. And really the only interesting question is, how many of these entangled qubit pairs do we need to make Alice and Bob win? And so it turns out that I think the answer is 3. That if they share 3 entangled qubits, they're good, they will win the game. And so this is a way of saying we can think about quantum games with 2 people on opposing sides. We can think about quantum games with people being on the same team, and we can do further generalizations of that. And this brings us then to the next question, which is what is an equilibrium for a quantum game? And there is a quantum game literature out there. A lot of what I find is 20 years old at the time, and of course is from way before quantum computers became real, and certainly before people even dared to dream about the quantum internet. And so it means that I think that we need to really beef up what we know about how to get how to even think about equilibria in quantum games. So some of the papers one can find are about taking classical games and then changing one of the players into having what I would call a quantum strategy, which is very fine. But I think we need to go into thinking about what is it that's needed for thinking about equilibria for something we can use, for example, for security games, and particularly quantum security games. And so I wanted to learn about that. So this brings me to my third point about where could quantum games be applied to security. And so I read a delightful paper from 2013 written by some of you, the Game Theory Meets Network Security and Privacy paper, that outlines 6 areas of success that people have had with developing security games and thinking about equilibria, thinking about how one can model these situations with players, game models, and thinking about what is the equilibrium for that game model. Is it a desirable equilibrium? And can we use that equilibrium to help design security protocols that will drive the system into a good, desirable equilibrium, such as what I found out in the paper, a Nash equilibrium or a Stackelberg equilibrium or something else. And then I asked myself the question, which of these areas would then be ripe for thinking about quantum security games, especially in the context of the quantum internet? And I have 3 suggestions. So here they are. Of course, all of these 6 areas have been tremendously successful for classical networking, but now we are talking about quantum. And so I want to touch on these 3 ideas here at the end. And so that's sort of the research agenda that I'm outlining. And let's start with security at the physical layer. And so you've already seen how the quantum internet is going to have some transmission of photons, some transmission of classical bits for the purpose of doing quantum teleportation. And so it means that there's some classical stuff and some quantum stuff going on. And so that's kind of what the players are doing. And now we can look at a jamming attack. So of course we could try to jam some of that, and the quantum people will have to think about how to secure that. And so we get many of the same problems as with what has already been done for the classical networking, but now there's quantum stuff going on in addition to that. And the question is, what is a good model? What is an equilibrium? What can we do there? So that's the first direction. Now let me touch on a different direction, which is trust. And so there was an exciting development last year where Urmila Mahadev at Berkeley, now at Caltech, solved a long-standing problem about, we can call it trust in quantum computing. And so I want to see where we can take that next using games. So what's going on is the following. So we are networking quantum computers, and we want to, they need to talk together to do big things. And the question is, maybe one of them is cheating. Maybe one of them is actually not doing quantum computing. They just make it look like they're doing quantum computing, but actually they're doing classical computing. And so the question is, what can the other parties do to trust everyone in the network, or trust as many as they think is right to trust? And so what Urmila Mahadev did was to develop a protocol. It's an interactive protocol, which is good for letting a user, even a user without a quantum computer, do something to exactly use. It's a crypto protocol. So to use a crypto protocol to be convinced that another party is actually doing quantum computing. And so the question here is, if we set up a model, maybe a game model, where we have a bunch of nodes, some of them may be malicious in the sense that they say they do quantum computing, but they do classical computing. And then we want to all the nodes to build trust in each other. How can we model this in a way so we can start to talk about an equilibrium where we get as much trust as, justified trust as possible, and still as little disclosure as possible. And so the reason for this disclosure question here is that Urmila Mahadev's protocol actually, it sort of puts a harness on the quantum computer in a way so that the one who wants to be convinced that the quantum computer is doing quantum computing drives the quantum computer to do whatever this person wants, or this player wants. And so this is maybe a bit much to require somebody else on the internet to be allowed to do that. And so we may need a game model here to sort of get all this under control, and so that we can develop trust in the quantum internet. Then the last direction I want to touch on is crypto. Of course we have multi-party computation, and I think that what we will see with the quantum internet is multi-party quantum computation, which is really a big part of the reason for why people are excited about the quantum internet to begin with. The whole point here is that it may be that that people at some point is going to run into a wall of how big quantum computers, in the sense of number of qubits that they can build. But if we can network a whole bunch of quantum computers and we can entangle qubits from one quantum computer to the next, maybe it means that just like today, the internet is making everyone's computers more powerful, maybe the quantum internet will make all these quantum computers more powerful. And so now the question is, if we're going to do multi-party computation in the usual sense that not every party wants to disclose everything they know, how do we get that to work? And of course, normally what happens here is that we apply cryptography to game theory, and then instead of having a trusted third party, what we have is some kind of distributed crypto protocol that allows everyone to participate in the computation in a reasonable way. And again, I think that games can model this for the quantum world. All the parties are doing quantum steps, and we need, again, to think about what is a good game model, what are the equilibria that will allow us to make progress. And one of the things one can find in the quantum game literature is that they do find new kinds of equilibria. So for example, they will model a zero-sum game, and they will find that because everything is quantum, new kinds of, for example, new kinds of Nash equilibria will show up. And so I see the potential here, so that's really my point. Quantum computing needs security, and we're getting to the point where we're going to need it soon. And I think that some of that security can come from quantum security games. And so here we're talking about jamming attacks, about trust, about multi-party quantum computation, and there may be many more. This is as far as I got. And so the field needs you. Quantum computing is expanding. It used to be a physics discipline, really. Now it's expanding into computer science and electrical engineering and other areas. And I think game theory is well positioned to take on a new angle on quantum security and get something done. And so I'm hoping that some of you will think about whether some of these research directions appeal to you. Thank you. I will be delighted to take questions.
Thank you, Jens, for a really interesting, clear and excellent talk. Thank you very much. You also brought several points that are exciting to the community. I have my own questions, but I'm first going to let the audience ask you some questions. Anyone wants to pose question to Jens?
I put some on the chat.
Oh, you put something on the chat. I was not looking at the chat at all.
I can say it. Okay, so the problem is this. Okay, I like very much your talk, but I have two questions. The first one is, we know, right, that to transfer or transpose or transmit or whatever you want to call it, entangled states, there is an energy constraint. And similarly for teleportation, and because of the Casimir phenomenon and all that stuff. So basically teleportation has been done by photons because energy there is very low.
Yes.
But so where are we in overcoming these energy constraints in real applications, and how do we verify them?
Yes. So the energy loss is the next big barrier to
Right.
getting this teleportation done. And so it means that the teleportations are so far done only in the lab. And so, for example, I saw Saikat Guha's talk just a few weeks ago, where he talked about that they want to achieve teleportation over a few hundred meters in Arizona. And that's sort of as far as they can get with getting really getting things done without the energy loss. So that, I think this is the next barrier. It's a real problem. On the other hand, I also want to say that the reason I'm excited, I mean, look, I'm a compiler guy in a sense, right? Classically educated, and the reason I'm excited about quantum computing is that this field is expanding and making progress so much faster than I had thought possible. There are things that are already happening today that I thought I would not see in my lifetime when I sort of expanded out 10 years ago. And so I think that things that look impossible today, they will probably be solved 3 years from today. That's how fast this field moves.
Great.
Now let me ask you a more controversial question.
Yes.
Okay. Because I've been struggling with this area for almost 30 years, starting back to quantum estimation. So we have an equation in game theory that's called Hamilton-Jacobi-Isaacs partial differential equation.
Mm-hmm.
And it can have two players, can have more than two players. That's a PDE, a partial differential equation. It's parabolic, it's nonlinear, and has a potential.
Yeah.
Now do what Nelson does. Take time and make it imaginary.
Mm-hmm.
This becomes a Schrödinger equation.
Mm-hmm.
So if you've studied Feynman, as I have,
mm-hmm.
Now I can try to do quantum computing the way Feynman advocated, meaning if I find a physical system whose Schrödinger equation is the one I just gave you, I have a direct implementation in hardware of a computer that solves the game. But that approach has nothing to do with qubits. And this is the controversial statement. So what is your opinion on that? I can send you a few notes on this, but this is something that I have always argued with people with qubits, because I don't know, qubits have limits. But anyway, I want to hear your comments on that.
it seems to me, okay, so you know this in a depth much greater than I do, but it seems to me that some of that, maybe there's a way that quantum computing can speed up some of this, but it seems like classical computing will do just fine in solving what you said.
No, we cannot solve this in classical.
Cannot solve it at all?
Impossible, no. So the idea is inspired by classical analog computation, where I don't know if you remember. If you remember when we were doing, you know, real computation with the resistors, inductors, and capacitors, what we will do, we write down the differential equations, and then we cook up a network with real resistors, inductors, and capacitors, or mechanical or electrical, and that would be real-time computing, all right? But we will never go through digital or anything like that, okay? This all disappeared, and I'm an old timer because we went to digital. So I'm going back this way. I'm saying if I take a PDE, which is Schrödinger. Schrödinger is still a good model. I can put qubits into Schrödinger, but I don't have to. If I find a system, a real physical system, whose Schrödinger equation is the one that describes my phenomena, I'm done. That's a computer that does real-time quantum computation of my physics. And this is true for several of the key equations you control, including the Bellman equation, the filtering equation, the game equation, and so on and so forth. And I've been asking people this question, and there have been only a few that they say, yeah, that's an alternative approach.
I see. So what people are doing classical is they find approximate solutions to these equations, right? They can
but I'm bypassing that because I find a physical system whose exact Schrödinger equation is the one I gave you.
Yes. Yes,
right?
I think that in many ways this is the same thing that quantum chemistry simulation is trying to do.
Yes, exactly. Right?
And so I would think that there's hope, but it sounds like we will need a lot of qubits to model what you're saying. That's the same problem that the quantum chemistry people have. They for the kind of things they want to do, they need something like 3,000 accurate qubits.
But you see, I'm not thinking qubits.
Right.
I'm thinking wave functions, not qubits.
Aha. Well,
see, I'm not using the discrete version of quantum mechanics. I'm going continuously, completely, wave functions. Yeah, I'm using probabilities, if you like.
Why the quantum computer should be very good at representing funky.
Yeah. It's just I wanted to ask you because obviously you thought a lot about these problems, and I wanted to see if you have run into this kind of idea at all. Anyway, thank you so much for a very great talk. Yeah.
Thanks.
Yes, Jens, there's one more question for you. This is from Mark Blinsky. Can you see that?
I'm sorry, I didn't.
Okay, no worries. I will actually read. It says, Jens, extremely interesting talk. Do you think there is an analog for quantum annealing that could apply to game theory as well?
Yes.
That's a good question. I must say that I have actually not studied this question. So I decided that quantum annealing is a more, let's call it impoverished model of quantum computing. I think that the games you would be able to model with quantum annealing would be very weak. But of course, it could also mean that this means that one could get more out of the math of doing it. But I think that the way the world is going is that we are moving away from quantum annealing and we are moving to what we could call these gate-based quantum computers that are underlying my talk here. So they are more powerful, and it means we can model more. I think that if there's going to be quantum games related to quantum annealing, I think that it'll be very little one can do there.
Great. Then thank you. And another question is from Tamer Bashar. Thanks for the fascinating talk. I have a simple question. Is there any connection between entanglement and correlated equilibria in games?
That's a wonderful question. I don't know the answer. I think that is a very fundamental question to ask. And I think that in many ways, this is where new strategies for the players in the quantum game can come in by using entanglement. And whether then that has something to do with correlated equilibria is sort of the next frontier. And so I think that already that is a sign that we have new questions we can ask when thinking about quantum games.
That's great. Thank you. And then I think this may be just an observation that the first point you mentioned as jamming attacks is naturally generalizes to your quantum internet, because denial of message attack falls into that. Any congestion games fall into that probably. So that could be, yeah, it's a good model to point out.
Yes, absolutely. Absolutely.
Great. Any other questions for our keynote speaker?
Amer, I have unmuted you. If you want to talk, you can talk.
Yeah, well, it's, I think something, thanks for, again, the wonderful talk.
Thank you.
And the more beyond the sort of connection between entanglement and correlated equilibria is the issue of information that the players have access to. I mean, in all the games that we have talked, they are essentially open loop. They are not sharing any information other than through entanglement. The question is, what sort of, in games, we know that information structures are very important. How much players know about others' actions or motives or behaviors and so on. So do you think that this additional knowledge can be integrated into the quantum computing framework?
Yes, I think so. Absolutely. So I think that's really where classical game theory and then quantum meet each other, and I could easily imagine that certainly with current engineering restrictions, for example, this thing of sharing two entangled qubits is expensive, and so that maybe one should study what if some players have a limited amount of shared entangled qubits, how much can they then get done with shared strategies? It could be an angle on that. And so I think this thing of sharing information, about having partial information about each other and each other's intent, I think I think there's a whole new dimension to it here with quantum.
I think it's a rich avenue for research.
Yeah, I mean, there's actually a very rich connection through the energy constraint, Amer. And another thing to follow up your question is that it seems to me that these untangled states are basically almost like non-partially joint distributions. I mean, I have several players, and I start getting information about joint distributions. With that now, without constraint, everything becomes much more useful. But we know from, at least in classical computing, this is very difficult computation. So, yeah. One last question I had is, one of the things I suggested to Rada is to look at quantum prisoner dilemma game. You know those, right?
Oh, yes.
So for those of you who try to look at this, we all know the application of prisoner dilemma in security, but read the papers of quantum prisoner dilemma. You'll be surprised about how many things you don't expect they actually get if the model becomes quantum mechanical. It's a simple introduction anyway. I don't know if you've looked at it yourself. It's more along qubits, but yeah.
I was actually thinking I would talk about the quantum prisoner's dilemma in one version or the other as part of this talk, but I couldn't get my math to work out. So I decided, well, I'm going to simplify it. But I think it's totally fascinating. I got an MBA a couple of years ago when I was on sabbatical. I was at UCLA's business school. And of course, as soon as we got to economics class, they start to talk about game theory and we get the prisoner's dilemma. And now I feel inspired that there's got to be a quantum version of this.
Yeah. Thank you so much.
Yeah, thank you again for such a wonderful talk and also good discussion. Very nice discussions.
Many thanks for inviting me. It was a pleasure.
Yeah, and just to close the loop, as we talked about, maybe we will have you sometime during the cherry blossom time in the spring at University of Washington.
Oh, that would be lovely. I look forward to that. Yeah. I will have to bring my wife. She's the one from Taiwan who loves cherry blossoms, and we don't have them in Los Angeles.
Oh, well, that's your advertisement, rather putting the picture behind. Anyway, so I think we are done for the day, right?
Yes.
So we'll see you all tomorrow, or whoever comes tomorrow, and maybe more. We start at the same time. Thank you all very much for coming.
Thank you, Jens. Thank you again. Thank you all.
Thank you. Bye. Thank you, Jens, very much. Thank you.
Bye.